Welcome to this course on Vectorbt. My name's Chad, and over the course of the next couple of hours, I'll be taking you from zero to hero in Vectorbt, all the way from literally having never used it before to being able to make your own custom indicators, backtest them, produce visualizations, so on and so forth. I know this library can be quite difficult for people because it's quite new and the documentation is not fully formed yet. So this is my attempt to help out. Now, what is Vectorbt, you might be asking? Well, it's a backtesting library in Python that we can use to test our strategies and how they have historically performed. You buy when an indicator gets to this point, you sell when it gets to this point. How well would that have done? But the magic of Vectorbt compared to all the other backtesting libraries is that it pulls in lots of common open source data science libraries that you've used before, and it uses those as its core components. So when you're building things in Vectorbt, most of the time you're actually dealing with a Pandas object or a Numpy object or a plotly graph. And if you've had any exposure to data science in Python before, you'll be very familiar with all of these different technologies and how to use them, thus speeding up your acquisition of the backtesting library such that you don't have to think about it too much. So what are we going to be covering in this tutorial? Well, we're going to start off just with the simplest possible strategy that one can run, and how to get up and running and backtesting in, it's like 20 lines of code. It's really quite stupendous how compact you can get your code down to if you know your Vectorbt library well. We're then going to think about how we can make our own custom indicators, because while using the built-in RSI and moving average and EMA and whatnot are quite interesting, most of the time you're not going to be actually using those indicators when you're doing trading, or you might want to combine different indicators together. And that's what I'll be covering in that section of the video. I'll be showing you how to build your indicators using something called the indicator factory, which is a component in Vectorbt that takes in regular Python functions and turns them into Vectorbt functions, which can do all the nice things that Vectorbt does for us. Then we're going to move on to hyperparameter optimization. So you've got some kind of strategy and it takes in some parameters. Because Vectorbt is so fast, or at least we can make it very fast, you can repeat these backtests thousands and thousands of times with slight variations to see what kind of parameters do well and which ones just don't tend to work very well historically. And there's also a number of really useful plotting functions that it brings over from Plotly, like plotting heat maps and volumes, so that you can visualize how well the different sets of parameters do. I'd say that parameter optimization is one of the highlights of this library and one of the things it really, really works well at. I haven't seen anything else do as well as Vectorbt on that particular point. The section after that will be on optimization techniques, since if we're running, maybe hundreds of thousands of backtests, it's well worth thinking about how we can minimize the computational resources required for each of those backtests, because otherwise you'd be waiting around forever, or it might consume all of your RAM and kill your kernel. So I'll be teaching you things like how to substitute in libraries like talib, which are more efficient, how to use the number just-in-time compiler, to use compiled code, which is much faster than just interpreted code in Python, and also how to split your backtests into a few different sections so that you don't run out of memory. The section after that, we'll be talking about graphing and dashboarding within Vectorbt. It's mainly going to be just pulling some Plotly functions together and diving through the Plotly documentation. I'd say that overall, graphing in Vectorbt is probably the low point, with the exception of the heat maps and the volumes that come with the hyperparameter optimization. But there's still some really nice options to create dashboards showing your profit and loss on each trade and that kind of thing that come built in, and they work really well. After that, we'll be covering order types. So we'll be thinking about how to do shorts as well as longs, and different kinds of stop losses like trailing stop loss, regular stop loss, take profit, things like that. We'll be looking at how we can implement those into our strategies. And then finally, I'll be giving you some tips on how you can avoid overfitting. Overfitting is something that is very easy to fall into with a library like Vectorbt that's so good at finding optimal parameters. If you go live with that strategy, you'll probably find that it doesn't actually work the way you intended because you've overfit to the data. So I'll be giving you a few tips in the final section about how you can avoid overfitting by running your strategy through lots of different time windows, as well as comparing your strategy to a control strategy using just random trading. If you want to grab the code for any of the tutorials that are in this course, it'll be in one of the blog posts which are in the description below. There you'll be able to find an updated version of the code just in case anything breaks, that kind of thing. So chapters are in the description. You can skip to any section that interests you the most. Let's go ahead and get going and build out a simple example. Let's get started here with our quick overview of Vectorbt and its components and all the various features that you'll find inside Vectorbt. So you'll want to keep a copy of the documentation up pretty much all the time while you're following this tutorial, in case you want to look up, say, which indicators are built in, different functions that I'll show you. There are some variations that you can find on the docs here that'll be helpful to you, and so that's vectorbt.dev. That's where you'll find all of the documentation. So let's pull up an empty folder here. So I'll just go into this folder called Quickstart, and I'll open up a terminal. Now, you'll want to make sure that you've got the correct version of Python installed. So I'm going to make a virtual environment here, just using virtual env. And I'm going to call it venv. If you're using a more traditional editor like VS Code or PyCharm, it will typically handle the virtual environment for you. So you don't have to do this step that I'm doing here. But the main thing you want to check is you want to check your version of Python. And as you can see, I'm on Python 3.8.10. As of the time I'm recording this video, so that is February of 2022, Vectorbt doesn't play too well with Python 3.10, which is the latest version. Now, this may be different whenever you're looking at this tutorial, but do make sure that the Python version you're using is explicitly mentioned on the Vectorbt GitHub. So you can see here it's valid for 3.6, 7, 8, and 9, but not 3.10 as of yet. So just make sure that that is the same. In a previous tutorial on Vectorbt that I did, some people had problems with that. So, okay, so we've got our Python set up here. We've got our clean virtual environment. Let's go ahead and just install Vectorbt. So you can do that with pip install Vectorbt. It'll take a few seconds. It'll also install all of the requisite dependencies that it uses. So you can see it's using SciPy, Pandas, all kinds of stuff. Numpy. Many different packages here. So for the most part, you'll be okay with just installing Vectorbt. You won't really have to install anything else, mainly because it installs everything else that you possibly want. Sometimes you'll have errors like these here. So you can see this one where it's telling me that I need a specific version of Numpy. So you can see I have version 1.2.2. That must be what automatically installed, whereas it actually wants a version less than 1.2.2 and greater than 1.1.8. So I'll have to fix that manually here in a second. So I can do something like pip install numpy == 1.20. That may or may not happen on your install, but it's just something to watch. Make sure you've got the right versions of all the packages. Now, that should be enough really for us to go ahead and get started. We might have to install some more packages as we go along, but we'll cross that bridge when we get to it. So we'll start off by just opening up a Python file. So I'm going to call mine just tutorial.py. We'll import Vectorbt as VBT. And the first thing we'll need to do, as pretty much always with these kinds of backtesting videos, is we need a source of information, so a data source. Now, Vectorbt comes with a built-in Y-Finance adapter, so you've probably used Y-Finance before. It's an adapter for integrating with the Yahoo Finance API with Python. And Vectorbt has a built-in adapter that allows us to connect to that. So in order to do that, we'll create some sort of data frame here. So I'm going to call mine BTC price, since I'm going to be using the Bitcoin price. And that's going to be equal to vbt.yfdata.download. Make sure you get your capitalization right there, so capital Y, capital F, capital D. You'll then want to give the asset name. So for cryptocurrencies, the format is the asset, and then the fiat currency pair, or if you were trading ETH BTC, maybe that would be the format. You can also just put the names of stocks in here. So if you wanted to, you could put Apple or Tesla or whatever kind of stock that you're looking to backtest against. Yahoo Finance should have some data on it. There's a few other options that we might like to declare here. So one of them is what happens if the data is missing for a particular index. I'm just going to say we're going to drop all that data. Yahoo Finance is usually okay. It usually doesn't have much missing data, so this is not too much of a concern, but we don't want null values messing up our calculations when we're trying to calculate some kind of indicator. So if I leave everything else as default here and I call .get close, what will happen here is if I print out BTC underscore price, is that we'll grab the Bitcoin USD price data, and it'll be daily data by default, and it'll just try and grab as much data as it possibly can, and it will get us the closing prices. So let's go ahead and try that. It looks like we need to install Y-Finance separately in order for this to work. Makes sense. So pip3 install Y-Finance. And in a few seconds, we should be up and running. It might ask us to install requests as well, maybe. Nope, that seems to have worked. So you can see Yahoo Finance has data from about 2014 for daily data for Bitcoin. Obviously, if you want earlier data, you'll have to go script that yourself from some other data source. I have plenty of videos on how you can do that on the rest of my channel. You'll notice that this is a Pandas series. So if I maybe print out the type here, so if I print type of BTC underscore price, this is the format that you'll actually want your information to be in. So if you're not wanting to use Yahoo Finance, if you want to use your own data source, maybe you've got some CSVs, or you're grabbing data from Polygon or IEX or any of the other data providers really, or directly from a crypto exchange, you'll want to make sure that the data that you actually get is in this particular format. So you have a date time index, and it's a Pandas series here. If you want to get information for more than one symbol, you can just pass a list in here. So we can do something like BTC USD and then ETH USD, for example. And if we give it a few seconds, that will produce two columns here, and that will actually give us a data frame, which obviously if we've got multiple columns, the series then becomes a data frame. Note that it drops all the data that is not in both of the data frames, so it aligned them. So obviously Ethereum doesn't have price information going back to early 2014 because it didn't exist back then. And so Yahoo Finance only appears to have information from 2017 onwards, and that's why it's cut out all the information before then. Just something to be aware of later on when we're looking at the results of our backtests. I'll return this back to the way it was, just using Bitcoin for now, but later on we'll use that there to just show you how easy it is to expand this backtesting for multiple symbols rather than just the one. We've got our price data now, so let's move on to doing some actual calculations of indicators. I'll leave the print statement there with the Bitcoin price just so that we can see that it's actually downloading and we can sanity check the information. Then we'll want to select an indicator. In this Quickstart section, I'm just using a really simple strategy. So I'm just going to take the RSI. So if I scroll down here, so if you go on the documentation, if you go to API, indicators, basic, you'll find a big list here. And if we go down to RSI, should be down here somewhere. I'm just going to be using the regular old RSI. I'm going to be providing a sell signal when the RSI goes above 70 and a buy signal when it goes below 30. Just as a traditional example that people would use using a single indicator. Later on, I'll delve into using multiple indicators, combining indicators, that kind of thing. But for now, we just want to learn how to use a single indicator to get our backtests up and running. So moving back to the Vim terminal here, let's set up our RSI. So we'll make a variable, call it RSI, and that's going to be equal to vbt.rsi. Make sure you use capital letters here, so you'll note that the functions are in capital letters. Make sure you use capitals. And then we want .run, so we're actually going to run some RSI calculations. Each of these functions has their own parameters that you'll need to provide. So I'm going to give it the BTC price, and we need to give that a window for the RSI, so it should say on the documentation here. If we go down to run here, you can see that it gives the inputs here and the parameters that you can provide, as well as the output of this function. Presumably it does the same for every others of the built-in functions here. The ones that we're going to concern ourselves with is the close and the window. Let's go ahead and implement that. So BTC price is going to be our closing data value. And then we'll also want to provide a window value. I'm just going to leave it as 14 for now. That's the default. We don't really need to change much. And if I print RSI here, you'll see what this actually looks like. So it's not what you would expect. Printing out the value of RSI doesn't actually give you the straight indicator information. It gives you all this crazy stuff about the indicator itself. If you want to get the actual values themselves, if you want to extract them, you'll have to call RSI.RSI, or equivalently for any other indicator that you use here. Something that might be a little confusing if you're just getting into Vectorbt, that if we run vbt.rsi.run, it doesn't actually give us the raw values. To extract the raw values, you'd have to do something like this. Now, the reason why it doesn't do that is because it's useful to just have an RSI object here, which we can call other functions on to create our signals. So I'll just show you that this is actually printing out the raw data here. So these look pretty convincingly like RSI values, and you can see the first few are null here because obviously we have a window length of 14. So the first 13 entries are going to be all nulls. So that makes sense. Everything looks reasonable here. And so the way Vectorbt works is that in order to actually create or simulate a portfolio, what we need to do is we need to provide a list of entry signals and a list of exit signals, or more precisely a series of exit signals and a series of entry signals. So we need to apply some kind of function to this series here that turns each number into a true or false value. So in our case, it's very simple. It's just, is it less than 30? then for entries it will be true. For exits, however, we only want it to be true when it's greater than 70, else we want it to be false. Now, the way we implement that is we use one of the other functions here provided on every single indicator. You can see we've got close crossed above and close crossed below. These are really quite useful functions. How it works is I can go over here and let's make a series and we'll call it entries. And I can say entries is equal to rsi underscore closed underscore below 30. That should give us a true-false series for the entries, where it will only give us a value of true when the RSI has closed below 30. Or rather, crossed below, and that's the one we want here. So if I change this to crossed here, RSI underscore crossed below. And then I print out the value of entries. And just to be safe, I'll change this to a string here, so to underscore string. That'll just print out every single entry so that we can examine everything. And apparently I misspelled entries. So the particular function that we used here was RSI crossed below. So as the name implies, this will only give a value of true when the RSI has crossed from being above 30 to being below 30. Even if it continues to be below 30 on an ongoing basis, it won't give any more values of true. This is perfectly fine for our particular strategy here, although even if you just wanted to use something like RSI below, I'm pretty sure with the default settings on going long only and going in with 100% of your position on each trade, I don't think it actually makes much of a difference. But in our case, we're using an RSI crossover strategy, so I'm just going to stick to being more explicit here. You want to do exactly the same thing with an exits series here. So instead of cross below, we want cross above. And instead of 30, we want 70. That'll do the exact same thing. It will just give us a true-false series of data for whether the RSI is above or below a certain value. Now, we're finally ready to actually simulate the portfolio. And to do that, all we have to do is, well, we create a variable and we call it pf for portfolio. And we'll set that equal to vbt.portfolio.from underscore signals. And now we provide our signals data. So you'll firstly want to give it some price data. That's going to be BTC underscore price. Then you want to give it your entries and then finally your exits. So what this function is going to do is it's going to take these buy and sell signals and just execute the orders as they come in. So every time the RSI crosses below 30, if it's not already long, it will open up a long position, and vice versa for exits. Every time the RSI is above 70, so every time exits has a true in it, and we have a long position, we'll close that long position. Now, if I run this, pretty much nothing will happen from our perspective here, sitting in the terminal. In order to interrogate this and to figure out what's going on, we need to start printing out some data, gathering some data from the portfolio itself. So from this portfolio object. The most simple way of doing this, just to get an overview of what's happening, is you can do pf.stats here. So you want to print that. And what that'll do is it'll print out a whole bunch of statistics about the simulated portfolio. So it'll give you Sharpe ratio, total return, how many trades were profitable, how many were unprofitable, percentage win rate, everything like that. It can be useful for just getting an overall grasp of what's happening with a particular strategy, if you don't want to go ahead with the trouble of actually plotting it out. It can sometimes take a few seconds to get started, but you can see we've got all this data here. So it's simulating daily data, got 2,700 candles, and we actually end up with a minus 15% return here, which is pretty terrible considering the benchmark return is over 8,000%. So that's just the hodl strategy. Our strategy managed to lose money even with no fees. If you want to look at how to add fees into the mix, you can check out the final section of this video. We'll have a section on different order types, how to make things more realistic, add slippage in, and that kind of thing. So you can see that overall this is a pretty terrible strategy, but it works for our purposes for just giving an example here. You can also just extract directly some of the metrics. So for example, you could print here pf.total_return, and that'll just print out the total return. So you can see we've got minus 15% here. You can also do a plot. Now, we'll be getting into plotting later on, but the most basic kind of plot you can do is to do pf.plot.show. That's the most simple kind of plot in Vectorbt, and if we boot that up, and give it a few seconds, it'll create a Plotly dashboard that we can use. So this is just working directly with Plotly itself. We're not doing anything overly fancy. And by default, it gives us these three screens here. So this one gives us our orders. So we can zoom in. We can see when we bought, when we sold, the details of each particular trade. This one gives us the trade P&L. So obviously, all the green ones here are profitable, red ones unprofitable. We can get an idea of the distribution of our trades, how they work. The final one here is the cumulative returns. So it's comparing the benchmark here, that's the hodl strategy, versus our strategy. Obviously, our strategy has performed absolutely terribly because we're missing all of these parabolic rallies. We're selling way too early into the rally, and we're buying too early on the dips. Just for fun here, I'm just going to add some more symbols into the mix just to show you how quickly you can expand your backtesting empire once you've gotten something set up. So imagine this is a much more complicated strategy that we're going to cover in the next section. To add another symbol and to compare them side by side, super easy. You just go in here and we'll get some different data. So we'll get some ETH data. Maybe we'll get some data for Monero. And we'll get some ADA data as well, ADA USD. Hopefully the Y-Finance API can keep up with that. And if I just run this, you can see we've got BTC, ETH, XMR, and ADA. It's going from the 9th of November 2017. Seems like they all have data from that point onwards. Might take a few more seconds to simulate here, but you can see that it's now given us a range of different returns for each of the symbols. You can imagine feeding in a big stock list of 3,000 different symbols and seeing which symbols your strategies tend to work best on and that kind of thing. Again, obviously this is it's not doing great for ADA here. We're down 97%. It's also interesting that it shows us the RSI window here. So just to give you a sneak peek of some of the parameter optimization stuff we'll be doing in a second, you can also just give it multiple windows here. So if I give it maybe 14 and 21, let's see what happens if I run this. So you can see it's just repeated the entire process, but for the RSI window of 21 rather than 14. And you can see that this is marginally better, but that's not the point. The point is to just show you the magic of Vectorbt in that all I did is I just converted this scalar value here to a list of scalar values, to a list of numbers. And everything worked exactly as I wanted it to in the background without me having to do some crazy madness in order to finagle all of the various data frames and join them together and stuff. Vectorbt handles that for you in the background. All you have to do is provide a list of values that you want it to check out. Just before I head on to the next section here, I'll show you how to get different time frames of data from Y-Finance. Obviously, if you're using your own data, this isn't relevant to you, but I'm assuming a lot of people will be using Y-Finance. So if you want to get different time frames data, the first thing you have to do is provide an interval. So I'm going to provide an interval here of 1 minute. If you want to find, what the time codes are for a minute, hour, day, so on and so forth, you can check these on the Y-Finance GitHub, or at least their Pi page has it up. Now, with an interval of 1 minute, we're only allowed, I think, 7 days worth of data. So we need to provide a range that we actually want to take. So I'm going to take the last 3 to 4 days of data. And to do that, we'll want to import date time. It's a built-in module. You don't need to install anything. And then we'll just create an interval between 2 dates. So I'll create a end date. So this is the time that we're going to scrape the data to. So end date, and that's just going to be equal to datetime.now. So we're going to scrape data until this second. And then the start date is just going to be equal to end date minus datetime dot time delta, and then however long you want to put in here. So I'm going to say days is equal to 3. So I want the last 3 days worth of 1 minute bars, and this should hopefully work if I pass them in. So we'll say start is equal to start date, and end is equal to end date. And that should just work if I run it. So we can see we've got data for the last 3 days here, minutely candles, if at all possible. It does seem that it doesn't have minutely candles for some of the symbols here, and so it's dropped them because of the instructions that we gave it. You want to be careful about that if you're using this information to inform some kind of strategy. Make sure that your data doesn't have any holes in it, but for us, Y-Finance is pretty good in terms of getting data to us. So that's it for this little section here. I've tried to give you a little taste of how Vectorbt works, how to quickly get started, how to use their built-in indicators. In the next section, I'll be showing you how to take this to the next level and create your own custom indicators, combining indicators, that kind of thing. So I hope you're looking forward to that, and I'll see you there in a second. Now that we've got to grips with the very basics of Vectorbt, we know how to ingest data, how we can plug that into one of Vectorbt's default indicators, and we also know how to convert that into signals which we can use to simulate a portfolio and calculate any stats we might need. The next step that we might want to think about is how we can construct our own indicators. And how do we get our own custom indicators to play nicely with the Vectorbt ecosystem in such a way that we can use all of the really cool features that Vectorbt has that lets us not worry about lots of low-level implementation details. For example, the way that in Vectorbt we can provide a vector instead of a scalar for a particular parameter value. So say, for example, in this case, they're calculating lots of moving averages. And if you want to calculate multiple moving averages, well, all you do is provide a list with the parameters that you want. Now, obviously, your indicator might not be a moving average, but you get the idea. If you wanted to calculate your particular function with 1 million different values for a particular parameter, you can do that just by plugging in a vector here with the required parameters. There's also a really cool option where you can take every combination of the parameters that you provide. So you can grid search basically to find the best performing parameters historically for your particular function. We'll be covering that more in depth in the next section. For this section, we're going to mainly focus on just how we can create indicators. But again, just to give you some more motivation for using the indicator factory, Another really cool thing that it offers is that we can pass in Pandas data frames or series complete with timestamps, and then behind the scenes, Vectorbt's gonna just pull out the time series as if it's just a Numpy vector, do its manipulations, pass it back out, and zip that all back into our series here. You'll see what I mean in a minute, but it basically gives us the speed that Numpy offers with the convenience that Pandas offers. So it gives us the best of both worlds here in Vectorbt, and it's a reason I'm really, really fond of this library. So without further ado, let's get started and produce some custom indicators. We're going to be making a few different indicators in this section. We're going to start off nice and easy, just maybe combining some of the indicators that are built in, but I'll also show you how to add your own custom indicators just using raw Python, and how we can combine different indicators together, as well as different timeframes by resampling our data. So let's go ahead and get started. So make sure you're in the virtual environment that we created in the last section. So you've got Vectorbt installed, that kind of thing. And then we'll go ahead and just create a file. I'll call mine tutorial.py. Now the setup here is going to be relatively similar to the first script that we made. Obviously we want to start importing things, so we'll import Vectorbt as VBT. We're also going to want Pandas as PD, and we'll also want Numpy here as well. If you're not familiar with Numpy, it's just like a lower level library for dealing with vectors and speeding up calculations. So Numpy as NP is a common abbreviation used. I'll be talking more about optimization techniques and how you should think about Pandas versus Numpy versus Number, which is another module we'll be discussing later on. I'll be discussing that later on in here. For now, we just want to get to grips with the syntax and not worry too much about performance. So we'll go ahead and grab some data again. Again, we're going to use the same methods we used last time. So I'll import date time, and then we'll do btc underscore price is equal to vbt.yf data, capital YF and D, dot download, and then provide the name. So I'm going to go for BTC USD data. If we have any missing data, I'm just going to get rid of it. So missing index is equal to drop start. Well, I'm going to set that equal to start underscore time. I'll set that variable in a second. End is going to be end underscore time. Interval is going to be equal to 1 minute. And we're going to get the close from that. So we've seen this all in the last section, nothing new here. I'm just going to create the start and the end times. So the end is going to be equal to datetime.datetime.now. And then the start is just going to be equal to, well, the end minus datetime.time delta. And let's say we want 2 days of data. So days equals 2. And then we'll print that out, and that should give us something nice. Print out our price data here. Of course, I have to make sure I name my variables properly here. So end time and start time. Okay, so that's great. We've got a time series here with the past 2 days of data roughly ready to go. This is Y-finance, so you'll notice that sometimes we're missing data here on the minutely candles. Obviously, if you're doing some super serious backtests, you'll want to make sure you're using a quality data source with all of these filled in, but Y-finance is good enough for us for now. The next step is going to be to define our function, which we want to use. So this is our custom indicator here. So I'm just going to call it custom. I mean, you can call it whatever you want. I'll call it custom indicator. And then you need to decide what parameters it's going to take. So this first example here is going to be very simple. I'm just going to take in the closing price And then I'm going to take in a window, and the window is going to represent the time period for an RSI. So I'm going to set that equal to 14 by default. And I don't think we need to set any other parameters right now, but we'll expand this later on and make it a bit more complicated. So let's go ahead and fill the body of this indicator out here. So it's just going to be a very simple RSI function. So I'm going to set RSI is equal to, and then we can actually just use the included Vectorbt functions in here. So vbt.rsi.run, and then we'll pick our values in here. So we'll give it the close, and we'll set the window is equal to window. And then the indicator here will just be the actual value of the RSI. So we'll return RSI.RSI. So not the most interesting function in the world, but it'll do as a placeholder for now. We then want to actually tell Vectorbt about our new function that we've made and what the parameters are and how to interact with it, essentially. So to do that, we create an indicator factory here. So we'll create an indicator object, and I'm just going to call mine ind for indicator. We'll be using it a fair amount. And I'm going to set that equal to vbt.indicatorFactory. You can provide some names here, so the class name. These aren't incredibly important, but I'm going to call mine combination. And we'll set a short name to be comb. These will pop up later on when we're analyzing the data. You'll see the short name here for some of the columns. The main parameters you want to focus on here is the input names. So you might have multiple inputs, but in our case, I'm just passing in the closing price here. So we just have a parameter called close. We also want to give the parameter names, so the param_names. Again, we only have one. That's just going to be window. And then we also want to provide the names of our outputs. So outputs names. If we had multiple outputs, again, we provide the full list, but we just have one. You can call it whatever you want. I'll just call mine value. So once we've done that, we've kind of specified the recipe, what goes in and out of this function. We now want to actually point to this function itself, as well as provide some default parameters just in case the user doesn't provide any. So to do that, we'll call from_apply_func. We'll then give the function that we want. So that's going to be custom_indicator. And then we'll provide a default for window here. That's just going to be 14. I think that's all we need for the minute. So if I close that on out, we should have a fully functioning indicator here. Now, the syntax for using this indicator is going to be exactly the same as when you use any other built-in Vectorbt indicator. And the reason for that is that these are all built with the indicator factory. So once you've got it set up, using it is just as easy as using any other Vectorbt function. And of course, you can stack them and use them within other functions, etc., etc. In order to actually create some values here, we're going to have to run this indicator. So I'm going to say res for results is equal to indicators ind.run. Then we need to provide our parameters. So we'll provide our BTC price. That's going to be the close. And we'll provide a window value as well. I'm just going to say 21. You could also leave that blank because we set a default parameter for that anyway. And then finally, we need to actually extract the values here. So I'll just print out res.value. So that was quite a lot there to take in, but there's basically three chunks to it. So you define the indicator itself. This is just a regular Python function. You can do anything you want in here. You don't even have to use the input. You can just create, say, random values in here and return them. Say if you're wanting to test random trades, you could build a function that just returns literally random values just to compare your indicator against and see if you're beating random chance. This would be a good way to implement something like that. It's just a regular Python function. You can do anything that you would normally do in Python in here. The main thing that you'll want to note is that the shape of the closing data might not be what you expect. We'll go into that in a bit more detail in a bit. But yeah, that's the first section. It's just a regular Python function. Second section here is you're providing the recipe of how to build the indicator function. You're giving it a name, you're telling what inputs go into it, you're telling the parameters, and what the outputs are called. And you're also providing some defaults, as well as pointing the indicator factory to the Python function. Finally, you've actually created the function. It's the same as every other Vectorbt function, and we're now in a position where we can just run it and provide parameters as necessary. So my output value was called just value there, and hence when I print res.value, it should just give me the actual values, all being well. So let's give it a go and see what happens. So those look like reasonable RSI values to me, nothing insane. So I'm going to trust that this is actually working here, which is great. So we've got our function here, but really since this is the default RSI, we didn't need all of this fancy stuff. We could have just simply ran the RSI function here. So let's do something a bit more interesting. Instead of just taking the basic RSI, let's take the RSI and a moving average. Maybe that'll give us a better indicator here. Let's rename this parameter to RSI window, just for clarity here. And then we'll also make another parameter called MA window. So we'll have a moving average window and an RSI window. And let's set the moving average to 50, let's say. We'll then need to update our parameters here. So it's going to be RSI underscore window and then MA underscore window. Let's get back to our Python function here and start building out this moving average. Again, this is just a built-in Vectorbt function, so it should be fairly easy for us here to get going. All we have to do is say MA is equal to vbt.ma.run, provide the closing value and the window value here, so that's MA underscore window in our case. Now we need a method of combining these. So the way that I tend to build my custom indicators at the minute is to output a signal value, basically. So we've got an MA and we've got an RSI, and we're looking to test on certain thresholds. So for the RSI, let's say we want it to be greater than 70 to sell and less than 30 to buy, and we only want to buy when the price is above the moving average. We can't really get that by just returning the indicator value here. It's much cleaner if we convert this to a signal. So let's say a signal that gives true or false values. Much cleaner to return that rather than returning the raw indicator values themselves. It also makes life a lot easier when we move to parameter optimization later on, when we're using lots of different combinations of parameters. This might not be the most efficient way of doing things necessarily, but I think for the overhead that it gives us, it's well worth doing. So let's produce some signals here from these values. You can do this in a number of ways. One way would be to just extract the values here. So I'm grabbing the actual values. So I'm grabbing the RSI value from this RSI object and the moving average from this moving average object. So I guess just to give you an idea, I'll actually print these out as RSI. We can see what that looks like at least. Of course, I need to actually provide a moving average window here. And I'll need to change this here. I'm not doing well here with my variable naming. Everything should run now though. that errored out there, but it should have at least printed out the RSI here, which is what we wanted. So this object here, so this vbt.run, so and so and so forth, up to this bracket, this doesn't actually give you the numerical list of RSI values. To extract those, you have to call .rsi on them. That's the point I'm trying to stress here. And similarly with the MA, you have to actually call .ma on it. You can iterate through these to establish your condition however you'd like. So you're very welcome to just do a basic for loop. You can just loop through each entry. So you could do something like this. So you could go over here and you could say, for x in range, length of RSI, and then, if RSI.eloc x is equal to 20, do this. You're more than welcome to do that sort of approach. It works pretty well, to be honest. And it's an easy way to just lay out your logic of what you want to do. The method I'm going to use is I'm going to convert everything over to Numpy arrays and use numpy.where. So let's go ahead and implement that. So I want to convert these values here to Numpy arrays. So .to_numpy. If I print one of them out for you, you'll see what it looks like. So you'll see that it just looks like a list of lists, basically. This is just the format that Numpy likes to work with, and we have this very nice helper function here called to_numpy, which works on all Pandas series. In order to produce our signal here, let's go ahead and just make a new variable. So I'm going to call mine, say, trend. So this is going to be the trend indicator. And I want a value of 1 to be an entry, so we're going to buy. A value of 0 is neutral. We're not going to do anything. We're not going to buy. We're not going to sell. A value of -1 is we're going to sell any positions that we might have. You can extend this concept, of course. You don't have to do 0, 1, and -1. You could go all the way up to 5 or -5. It's just an easy way to combine indicators here. So we'll do numpy.where. Now you want to establish some sort of logical condition. So for now, I'm just going to use the RSI, but I'll implement the moving average in a second. We'll say where the values of RSI is greater than 70, well, then I want to provide a -1 value. Elsewhere, I just want it to be 0. So if the RSI is greater than 70, put -1 into the trend variable. And if RSI is not greater than 70, if it's less than or equal to 70, then just provide a value of 0, a neutral value. We'll do the same thing here, and we'll set trend is equal to numpy.where, except this time we'll use less than 30. And for there, we'll say enter. So when the RSI is greater than 70, exit. When it's less than 30, then enter. We don't want 0 here, though we want to provide trend. So that'll preserve any exit values that we might have had. And then let's just return trend here. And all being well, we should now, when we print this out, actually see our trend values rather than the RSI values. So obviously that's providing a load of zeros there. That means nothing particularly interesting is happening during that time period. So if I do .to_string here, that'll print out the full thing with all the data, and we should see some 1s and -1s. So you can see that this here is a period where we would be exiting positions. Here there's a time where we would add to a position, so on and so forth. You could also print out the original array here, so just the actual RSI values. You could return that alongside it, and you could print those out just to check that everything's okay, but I'm going to trust in my program here. We also wanted to implement the moving average into this system here. So I can go to our entry condition here, and I can say, well, I want the RSI to be less than 30, and that's one of my buy conditions. But another one of my buy conditions is going to be that I only want to buy when the price is below our particular moving average we've created. So close is less than MA. Numpy just uses a single AND here to determine like a logical AND. So don't use Python AND or I don't believe those work. I think you want to use the Numpy version here. So AND or I think OR is just going to be a straight line like that. So AND close is less than MA. Let's see if we get any errors. Nope, that seems to have worked. It'll go through and compare element-wise close and MA, returning a 1 if it's true, and of course this is true as well. If not, it'll just keep the original value of trend in there. This is possible because of the format that Vectorbt passes in this close here. So you'll note that we're passing in the data as a Pandas series here. BTC price is just a Pandas series that we pulled from this data frame over here. But if we were to go print out the value of close, so print close, you'll see that it's actually just an array. It's just a straight up array here, so it's a list of lists. The reason why it's provided like this, so you'll notice that there's an outer list and then lots of inner lists, and each inner list only contains one item. The reason for that is if we have multiple sets of price data. So I'll show you what happens here if I just go pull, say, some Ethereum data as well. If I pull some Ethereum data, the close price now has two entries. On the left has the Bitcoin and on the right has the Ethereum. So do be careful that if you're writing your own functions here, so if you're not using any built-in Vectorbt function or Pandas function, make sure that it can handle this format for ingesting raw price data, and that it can handle as many columns as you want. Obviously, if you only need one column, you only need to worry about that, but I just thought I'd mention this. It's something that can trip you up when developing custom indicators. You'll want to make sure that your function can handle this. All of the default VBT indicators like RSI, MA, they can all handle that format, as well as the wrappers around talib that it has as well, but we'll talk about those in the optimization section. Just for completeness sake here, I'll go ahead and actually convert our output here to signals that VBT understands and simulate a portfolio, just so that we can see some results at least. So we'll say entries is equal to res.value is equal to 1.0. And then we'll do the inverse for the exits here. So exits is equal to res.value is equal to -1. We're taking our signal indicator, finding where it's equal to 1 and 0, and in our case, those correspond to our entries and exits, because we're just using this one indicator. We'll go ahead and build a portfolio here, saying pf is equal to vbt.portfolio.from underscore signals, btc underscore price, and then entries, exits, and that'll do, I think. And then if I print out pf.stats, we'll get some sort of output. I forgot that I provided two tickers there, so we'll see what happens. I think it might have averaged the two of them. That's usually what happens when you provide multiple columns, but you don't specify what to do. If I just grab total return instead, we'll be able to see the values separately for Bitcoin and Ethereum. So we can see there that this strategy is not amazingly effective. We've succeeded in losing 1% and 4% respectively for BTC and ETH. Let's say we want to make this indicator even more interesting and complicated. We actually want to add an indicator on a different time frame to one that's our data is actually in. So our data is in 1 minute time frame here. But what about if we want this RSI to actually be, say, the 5-minute RSI, and we want to combine that with our moving average here? How would we go about doing that? Well, the easy method here is that we could start using Pandas functions here instead of Numpy. So as I said before, if we go ahead and print out close here, we'll see that close is actually just a Numpy array. And, well, that lets us apply Numpy functions and things that can take Numpy functions. But in order to resample this data from 1 minute to 5 minutes and then back to 1 minute and make sure everything stays aligned and nothing blows up, I'm going to be using the pandas.dataframe.align function here. Now, as far as I'm aware, Numpy has no equivalent function that we could use. And so we are going to lose a bit of speed here because we're using pandas and we're converting backwards and forwards. But that's the price you pay for having a more complicated indicator. Do let me know if you have a better way of doing this in the comments. But this way works quite well for what we need. And as long as you don't need some blazing fast assembly level code execution, we should be fine here. What we'll want to do is we'll first want to provide a parameter here to from apply func, and the parameter we want to apply is keep underscore pd equals true. So as the name suggests, that will make sure everything stays in pandas format rather than converting to Numpy arrays. And unfortunately, a lot of our stuff over here is based on the assumption that we're inputting Numpy arrays, but we'll cross that bridge when we get to it. For right now, let's just look at the value of close here and just see what happens to it. So it should just be in pandas format. So there we go, we can go over here and we can see that close seems to be just regular old pandas data frame, which is what we're after. Interestingly, nothing broke later on. Maybe it does some implicit conversion there. But let's continue to focus on this. So the next thing we'll want to do is we'll want to convert this to the 5-minute time frame. It's pretty easy with pandas, you just use pd.resample. So I'm going to create a new data frame here and I'll call it close underscore 5 minutes. And that's just going to be equal to close.resample. And then we'll provide 5 minutes. So you can do 5min like that, or you can do 5t. There's a few different syntax that you can use depending on what kind of thing you want to provide. 5 minute, 5 day, 5 year, so on and so forth. Now that should have just resampled it all. So if I print out close 5 minutes here, we're not actually using it for anything, but it should still work. You can see it's printed out a datetime index resampler here. That's because I forgot to provide a function. So when you provide a resample here, so resample it to 5 minutes, it splits it all up into 5-minute buckets. And you need to tell pandas which one of those elements in the bucket should represent the bucket. So I think since we're using close data here, we should probably use the last element. Let's print that out and make sure that makes sense. So that looks sensible to me here. We're just converting these 1-minute candles. We're taking a group of these 5, and then we're converting that into the 5-minute candle here. So these 4 get represented as this candle, which I believe is the behavior that we're after, although when it comes to things like this, everything can get very horribly complicated, so do make sure for yourself that your data frames are properly aligned and resampled exactly as you'd like. So we've got our 5-minute RSI now. So that's great. What I'm now going to do is I'm going to run that through our RSI here. So rather than using close, I'm going to use close underscore 5 minutes. And we're not going to convert to Numpy at the end here because I'm going to do some other stuff. I think just to prevent any errors popping up, I might just comment this out and maybe return a scaler, and hopefully that'll broadcast to the correct format. We've got close here and we've got close 5 minutes. Let's instead print out RSI so we can get some idea of what's happening here. RSI, and we'll also print out close just to compare later on after we've done some manipulation. Running this. Over here, we can see our RSI function seems to be functioning. These look like relatively normal RSI values. So that's all good. One thing you will want to be aware of here, because we're converting minutely to 5 minutely, is that, so because this bucket here only has one of the candles, you're kind of dealing with incomplete information. So do make sure when you're loading in your information that you're using complete candles and that it's not clipping as it is here. But this is just a demonstration, so it's not too important. Just something to watch out for in your own programs. But other than that, everything seems to be working great here. And we're now ready to downsample this back to 1 minute data. The reason why we're going to do that is because otherwise we can't do this comparison here. So this comparison is going element-wise through each part of the RSI, and then also checking that the close is less than this, again element-wise. Basically, we need this RSI to be the same shape as our input values. Now, the way to do that is to use pandas.align. So let's go ahead and try that out. I'll keep printing out RSI and close here just so you can see what happens. Now, if we go and look at the syntax for RSI.align, you can see we have left, right is equal to df.align, and then we have our various options in here. So we can use this by saying RSI blank is equal to RSI.align with close. And then we're going to want to start looking into the options here. So the main one which we're interested in is the broadcast axis. Now, broadcasting may or may not be something that you've come across before. Basically, what this is going to let us do is it's going to let us match up those 5 minutes into the 1 minute candles. So it makes sure that they're all properly aligned. Again, it'll be easier once you see the results, so I'll just keep going here. We'll also want to think about the method which we fill in nulls. And we'll also want to think about the join that we use. So the broadcast axis is going to be 0. It's going to be the index. So I'll try that now and see what happens. So broadcast axis is equal to 0. I'll just put this on a separate line for convenience. So you can see what's happened here to the RSI here. Now there are lots of nulls here, but ignore those for now. It's like everything's being spread out again back to the 1 minute time frame, and when there are available slots that can be matched between them, they're matched. So this one is the 6 o'clock bar here, and that's matched up to the appropriate amount here. If I print out to a string, we'll see that there are lots of others. So if I do to_string, we'll see it's matching on every 5 minute interval, basically. So you can see that every 5th one, it's aligning with the appropriate bar in close. So we're almost at the behavior that we want, really. All we need to do is forward fill this. So basically these three should have the same value as this. And then we'll also want to deal with the fact that this data frame is larger than this data frame. We actually want them to be the same size, but let's forward fill first. And if I go, remember the syntax over here, it's going to be method and then forward fill. Method equals forward fill. Running that, you'll see that they're now all forward filled. So we'll have the same value 5 times in a row, basically. Sometimes 4 times in a row if you've got missing data like we have here. But that's fine. It's just accurately representing what we had in our 1 minute bars. So if it's missing in the 1 minute bar, we also want to be missing over here, because we want these and these to be the exact same shape so that we can compare them element-wise. This stuff can be a little bit confusing, but just try it for yourself, mess around with the pandas functions, and you'll get there. The final thing to do, of course, is to now make sure that they have the correct number of rows. You'll notice that there are values in here that aren't in here. If we go back to the first element here, so we go to 11 minutes past 6, we just scroll all the way up, we can see that this one has a 10 minutes past 6. Now, we don't want that. We want them to be exactly aligned. And to do that, we just change the join method. So the default join method, I believe, is an outer join, which just gets all the combinations, basically. I'm going to use a right join here. So if we use, I think it's join underscore method, or just join. Join is equal to right join. So what that's going to do is it's going to take the keys from the right table only. So the right table is going to be closed. So this is the left table, this is the right table. And so ideally, RSI, RSI should be the exact same shape as close is now. If I get rid of this to underscore string here, it should print that out for me and tell me that they're actually the same size. So it's 2003 rows, and this is also 2003 rows. We can see that they start on the same value, and they also end on the same value. So that's great. That means that all our data is now aligned, except that this is using the 5-minute RSI, whereas any values derived from this will obviously just be using the 1-minute time frame. So we can now proceed pretty much as normal after that horrendously complicated bit of aligning. So I'll uncomment all of this and just get rid of all my printing. This doesn't need to change. This is going to continue exactly the same as it was before, because it's just using the value of close and outputting a Numpy array. This will obviously be the 1-minute close. Just to make sure everything works in this section as it did before, I'm going to convert everything over to Numpy at this point. You might not necessarily have to do that. You could just stick with Pandas and convert this to using some Pandas function instead, but just to make sure everything works, I'm going to keep everything in Numpy format. So we'll say close is equal to close.to underscore Numpy. And we'll also say RSI is equal to RSI.to underscore Numpy. Now, if I'm not mistaken, when I run this, we shouldn't get any errors, and we should have successfully integrated 2 different indicators using 2 different timeframes within a single function in the indicator factory. Now, there are certain gotchas that you've got to be careful of, like I mentioned, with if you're missing some data that goes into a bar and you can have incomplete bars. That can be a real headache, so do make sure that you're using a good quality data source and that they align properly. So in our case, that would be that your 1-minute data source doesn't have any missing bars in a 5-chunk interval. You want to watch for that kind of thing. I'll print out the toString value here of our signal indicator just to see if we're actually getting any trades. Presumably we are, because it seems to have made some trades. But one would imagine, since we added slightly more intricate entry signaling, it's not as common. So that's the basics of this indicator factory and how you can use it to combine different indicators together. We're going to be using the indicator factory throughout the rest of this tutorial. So do take some time to get accustomed with it, build different indicators. And in the next section, I'll be showing you how we can really easily use this custom indicator that we've built, and we can optimize these parameters. So we can find the parameters that have historically resulted in the largest return or whatever metric we happen to be interested in. Basically, we're going to learn how to overfit this to an incredible extent. And I'll show you how we can test hundreds of different parameter combinations really easily. We don't even have to make any real changes to this indicator. We can just let the indicator factory do it all for us with a few extra parameters. So with that being said, I'll see you there. In this section, we'll be learning how to optimize the strategies that we've created. In particular, we'll be looking at hyperparameter optimization. So our strategy took in the window lengths for the RSI and the moving average. If we were to change those, we might very well have gotten a different return. And Vectorbt makes it really easy to check a wide variety of different values for both of them. We could even optimize things like the entry and exit points, given the way that we designed our indicator. We could easily add those as parameters and see what would happen, say, if we had an entry point of 25 versus an entry point of 30. Now, there are two main things to think about when we're trying to optimize our parameters. The first one is going to be performance considerations. So we're going to be calculating the values of our new indicators, maybe tens of thousands of times. Understandably, this can take up a lot of RAM and can take a lot of computing time as well, especially when we're simulating the portfolios and calculating profit and loss and that kind of thing. We'll be dealing with optimization techniques in the next section. So if you find that you're running out of RAM or something similar, do have a flick over to that section and I'll show you some techniques that you can use to reduce the amount of computation necessary, to use compiled code rather than interpreted code, and how to split things up into sections. So that's the first sort of word of warning. And then the second one would be, given that we're optimizing on a specific set of data, something like this is very prone to overfitting if you're not careful about it. And again, we'll be covering that later in this video. So you might want to check that section out just to get a reality check on your strategies and that you haven't just overfitted it to death. So without further ado, we'll get started here on parameter optimization. Generally speaking, when we're doing some kind of optimization, we want to get some kind of pretty graph out of it that we can show to people. And the main two kinds that we'll be using at least are the heat maps and the volumes. You can, of course, also use regular graphs if you want to. It's pretty easy to do that in Vectorbt. But these are the ones I'm going to be using. Now, heat maps, obviously, is a 2D grid. So it's great when you've got two variables that you want to consider, and then the color is going to be your metric. So maybe it could be total return. On the x-axis, you could have the value of one parameter, and on the y-axis, you could have the value of a different parameter. You can also implement a slider. So at the bottom here, you could implement a slider that would let you check different assets and generate the heat map for the same assets. So basically, a heat map is good when you've got 2 or 3 different variables that you want to plot against each other and compare. The volume is obviously a 3D plot. So that's going to give us by default 3 different variables, one for the x-axis, the y-axis, and the z-axis respectively. And again, you can also implement sliders with this. That's going to give you another variable that you can use. So volume's nice when you've got 3 to 4 parameters that you want to test out. That's just a higher level overview of the types of plots that we'll be producing in this section. Let's go back to our example that we made in the last section and do some optimizations on it. If we head on over to the terminal here, I'll go ahead and open up that file that we were working on last episode. And so we have this indicator that we made that combined the RSI on the 5-minute time frame with the moving average on the 1-minute time frame. To show you how easy it is to test different combinations of parameters, we'll try a few different values for the moving average here. So you can see by default it's set to 50. And if we head on down to the run here, we can see I also set it to 50 here. So just to show you how easy it is with Vectorbt once you've got everything set up, I can just turn ma_window here into a vector rather than providing a scalar. So I can just give a few different values here. Maybe I'll give 21, 50, and 100. Now, all being well, when we print out our total return here, it will give us the total return separated by 3 different sets of windows. So you can see in our final plot here that we've got the RSI window. So we only had one value for that. So that's going to be the same throughout all of them. We have the moving average window separated by each symbol. So that's pretty cool. The way to read it is to say this is the 21 RSI window with the 50 MA window for BTC and for ETH respectively. Obviously, changing the window here seems to have made absolutely no difference to this strategy's performance or which trades it took. Maybe we'll have more luck if we change the RSI window. So we can also change that here. So we can make that into a vector. Let's say I want 14, 35, and 21. Just pick some random numbers. Now there are a couple of different parameters here that we can set. I'll just run this in the default mode so you can see what's happening. I'll also comment out this because we don't want to print that out. So that finally appears to have actually affected some change in our strategy. Now you can see what's happened here is it's pairing them up in the order that I put them in the list. So it's giving us the RSI window of 14 with the moving average window of 21. And then it's for each of the symbols. And then it does the same thing with the next pair and the same thing with the next pair. This can be the desired behavior that you want depending on what kind of strategies you're wanting to run and if you need very specific pairs that only work with each other. But generally the behavior that you want is that you want to try out every combination of RSI, moving average, and symbol. So you want to know what the 14 RSI with the 50 MA looks like for both of them. Again, you want to know what the 14 RSI looks like with the 100 MA for both of them. And right now we don't have that. Luckily, there's a very simple option in here. So I add my comma in just to make sure. And we use the parameter param_product is equal to true. Now what that's going to do is it's going to take the Cartesian product of these two vectors here. So it's going to take every single combination of these three. So that should give us, I think, 9 combinations. And then, of course, we've got 2 different symbols. So it's going to run 18 different backtests. And I'll show you what that looks like. So there we go. You can see this is printed out considerably more backtests than the previous one. We've gotten each of the separate RSI windows combined with each of the moving average windows combined with each symbol. So we should have 18 if you go ahead and count them all up, because we've got every single combination of the 2 vectors. So that's pretty cool. We've got 18 different backtests. But I think we can push this a little bit further. To do that though, we'll have to modify our strategy a little bit. So we'll go back here and we'll add some extra parameters in perhaps. So in our function here, we've got RSI window and MA window. I think I'd also like to see what happens when we mess about with the RSI entry and exit. So I'll define a variable called entry, and I'm going to set that equal to 30 by default. And I'll do the same for exit, and I'll set that to be 70 by default. Remember, we do have to change the recipe that we give the indicator factory here. So we also have to tell it about entry and about exit. We'll also obviously have to implement it in our strategy here. So for us, that's just as simple as changing the hard-coded value to the desired variable. Some entry, and that should be good. And then finally, we'll want to provide some defaults here. So entry is equal to 30, exit is equal to 70. And then we'll also want to provide our values here. So we could give entry is equal to, we'll just give 2 values for now. We'll say 30 and 40. And then for our exits, we'll say that's equal to 60 and 70. Now, thanks to the magic of Vectorbt, it should just implement every single possible combination of all of these. So we had 18 backtests before. We've now got to add every single possible combination of entries and exits. So we should end up with 72 backtests this time around. It probably won't print the whole thing out, so I'll do a .to_string here, just to make sure it prints out a full total return matrix here. So you can see this is considerably larger than our previous backtest. Again, we've got every single combination of every single variable. Now, this can get a little bit difficult to read here. It can be difficult to find which ones are giving you the metric that you want. So in order to get that collection of variables as well as the result, you just have to print a few things out. So we'll save our total return here to a variable. We'll just call it returns. We'll get rid of the toString. And then we'll print out returns.max. Obviously, we want the largest return. We'll see what that is. And we'll also print returns.idxmax. That's going to give you the set of parameters which produces the largest return. You'll see what I mean when it's printed out. And I'll also print out the returns series here just to see what it looks like. So .to_string. I'll put that above the other two, otherwise it's going to print out a bit dodgy looking. We can see here it's just given us the best possible return of all of these different strategies, that being a stellar 3.1% for Bitcoin USD. And it also gives us the list of variables used to produce that value. The order of these variables here is going to be the same as the columns. So the first one is going to be the RSI window, the MA window, then the entry and the exit, and then the symbol. This has just given us the values for BTC USD here. If you want to find the values for a different symbol, then I think the easiest way of doing that would be just to filter out this series here by the symbol. So we could do that by going over here and just saying returns is equal to returns, and then returns symbol. Although I guess it's not a column here, so we'll actually want to get returns.index.is in, and then provide the values that we want. So it's just going to be ETH USD, and then provide the level. So for us, that's just going to be called symbol. That's the column that we want, the column of the index, that is. So that should work, and it'll just give us the returns series, but only with ETH data, and therefore we can find the maximum returns for ETH. There might be a simpler way of doing that, but that's just a quick and easy way to get the returns for a specific symbol, whilst also retaining all of this. You could, of course, wrap this up in a little function and just repeat it for every single element, and you'll get your maximum returns. Now that we've covered the very basics here, I'll go ahead and comment this little section out. And instead of just providing straight up lists here of different values, I'm going to use Numpy to generate some. We have imported Numpy here, so I can go ahead and use it. And we'll say the RSI window is equal to numpy.arrange, and we'll say between 10 and 40, and step is equal to, let's say, 3, and the D type we want to be an integer, because the window will only allow integer references. I'm just going to copy this, and I'm going to use this on the next few lines here. So the MA window, we might move this between, say, 20 and 200 in steps of 15. It doesn't really matter. We'll do the same thing for the exit here, and the same thing for entry. So entry will maybe have a range of between 10 and 40 is fine. I'll bump this up to 4, and then I'll bump this up to 4 as well, and this is going to be between, let's say, 60 and 85. So numpy.arrange, if you haven't come across it before, all it does is it just generates a numpy array of evenly spaced values between your two endpoints here, so between 10 and 40 in this case. In this particular instance, step apart. So they're going to be 3 apart. So it should generate 10, 13, 16, 19, so on and so forth until it gets to 40. And we specify the D type here just to make sure they're all integers. Some of them, I guess, don't have to be integers. The entry and exit could be floats. That's up to you. You can make that decision. But I would recommend specifying the D type here no matter what you need it to be, just so that it'll properly work when you feed it into your indicators. This will take a significantly longer amount of time to compute. Obviously, the higher the step value here, the smaller this array is going to be, so the smaller amount of combinations you're going to have to test. Let's run this and just see how quick it is. Apparently, I spelled arrange wrong here. It's arrange, like a range of data, rather than arrange like I'm going to arrange my files. So with that out of the way, it should work if I press run. That took quite a while there to simulate on my system, maybe a minute or two, so I'll bump down the steps. But you can see that we've simulated rather a lot of different possible portfolio combinations here. Although interestingly, the return hasn't actually gotten much better, even despite our incessant overfitting here. So I think with this, you've got the basics of how you turn your custom indicator into something that you can do parameter optimization for just purely by providing arrays here instead of scalar values. And of course, we can get the metrics here just by calling the function. So in our case, we've got the total return, but there's nothing stopping you from extracting the Sharp ratio or the win rate or any other of the stats that get printed out when you call pf.stats. All of those are available to you. You just have to find the correct keywords for it. You can find the full list on the documentation here. So if you go to the portfolio section and then base, and then you find metrics here, you'll find all of the different functions. So we should be able to find total return. That's here. This is the function that you'd call. If you wanted to instead get the drawdowns, or you wanted to get the amount of trades, or the trade P&L, the win rate, you can call any of these different functions and it'll calculate them for us in a nice Pandas series just like we have with total return. I'll stick with total return for now just because that's the thing we really care about. And it's all well and good having this data here in a big Pandas data frame, but we want to have a nice looking graph. So let's think about how we can use those two graph types that we learned about earlier, the heat map and the volume. So we'll start off with the heat map, since I guess it's simpler since it's in 2 dimensions. Now, obviously the heat map only gives us a 2-dimensional analysis. So what I'm going to do for now is I'm going to limit us to a single symbol. So I'm just going to get rid of the ETH data just by filtering that out there. And I'll also comment these out here. So I'll comment out entry and exit. So it should now just run with our default entry and exit values. So there we go. We've got 2 variables here which we care about. Let's go ahead and plot them out. So firstly, you'll want to note down the names of the columns here. I'm just going to copy and paste them so I don't forget them. I'll just put them down here in a comment or something. And then once we've got that, we're ready to just call the heatmap function. Very simple in Vectorbt. So you create a figure much like you would in Plotly. Of course, the base underlying plotting done in Vectorbt is done through Plotly. So you're going to see a lot of similar conventions in plotting in Vectorbt. So we'll say fig is equal to returns.vbt.heatmap. And then you give which one you want to be on the X column and which one you want to be on the Y coordinates. So we'll say X underscore level. Well, it doesn't really matter, to be honest, for our purposes, but I'm going to say the X is going to be the RSI window, and the Y level is going to be the moving average window. That's pretty much all you need in order to get a basic heat map running. Make sure you call fig.show at the bottom, otherwise nothing will actually appear. If I run that, we should get a nice Plotly heat map appearing for us. So there we go, our heat map appears to be functional. You'll notice it's very stripy here. So what that's telling us is that the value of our moving average window here is doing absolutely nothing to affect the total returns of the strategy. Just the way we've implemented it, it's really not making much of a difference. I mean, you can see the absolute value here is changing. So this is, minus 0.0036, and this is minus 0.025. So there is a small difference there, but what this heat map's telling us here is that the MA window is doing absolutely nothing. To make this a bit more interesting and just to show you what the heat map actually looks like, I'll maybe use a different variable here. So we'll try using the entry and plotting that instead. So that should be pretty easy to do given all our infrastructure that we just set up. So I'll just enable the entry point here. I'll comment out the MA window and I'll just rename this to entry. And if I'm not mistaken, that should give us a slightly different heat map that might be a bit more interesting. There we go, that's a bit more interesting, shows the two-dimensionality of the thing. And we can get some sort of general idea of which sets of parameters work and which sets of parameters don't. Obviously, we're overfitting it to death here, but it's nice for getting a good idea of just whether your strategy is worthwhile, what kind of parameters work and which ones don't. Let's get a little bit fancier with this graph now and add a slider in. So if you just remember, I got rid of all the ETH data using this line here, just by looking in the index and checking that it's equal to BTC USD. We don't really need to do that. What we can do instead is add a slider level here. And I'll set that to symbol. And what that will do is it'll create a slider on the bottom of the chart that will let us look at different assets, basically, and how it performs between the different assets. So it's essentially a sneaky way of plotting a third variable on a two-dimensional graph. So I can slide this between BTC and ETH and see how it holds up. This works dynamically if you want to use any other assets. So I'll go back to the top here, and I'll also pull data for Monero USD, let's say. And you'll see that will automatically add itself as another plot. There's no reason you couldn't do this with 100 different symbols and scroll through them like this and see which ones work. There's even facilities to make animations within Vectorbt, although that can get a little bit complicated, so for now just sticking to these heat maps is probably preferable. So that's the slider and how to use it. You just provide it as a parameter and it lets you plot an extra variable basically on a 2D graph. I'm going to get rid of these other assets here, or at least the Monero data, just to speed up the computation, because I'm about to do something a bit more intensive and I don't want it to use all of my resources. For now, we'll just comment out the heat map here. And I'll show you a trick that we can do if we have lots of different parameters that we're optimizing. We can aggregate across one of those parameters and plot that as a 2D graph. So say if you have 5 variables, you obviously can't plot that very well on a 2D graph, even with the slider. So how do we represent that? We can group by specific axes. So I'll show you the text version of this, the series printout, and then I'll show you how to implement that into a heat map. So on top of our printouts here, let's do returns is equal to returns dot group by, and then we pass in the levels that we want to group on. So level is equal to, and this can be a list with as many elements as you want, and the indexes that you put in here are going to be the indexes that you want to keep. So let's have a look at our different variables. We've got 4 of them to choose from, 5 if you include the symbol, so we need to trim that down to 2 or 3. I'm going to pick the entry and exits just to see what will happen. So we'll have to give it the comb_exit and comb_entry. So what this is doing is it's going to give us a heat map grouped by the exit and entry values. So you need to provide an aggregation function here. I'm just going to say mean. So it'll run all of these simulations, and for each entry and exit pair, it will average the results of all of these. Might make more sense when I go ahead and print it out. In this case, it'll actually also group over the symbol as well. So the average return between the 2 symbols will be averaged out. We might not necessarily want that, so I'll add the symbol here as well, and we'll print everything out. With these results here, you can see that we now only have 3 columns, and across the other 2 columns, it's just averaged everything out. So this combination here represents the average for all of the different RSI window values and all of the different moving average window values for this particular set of 3 parameters. So these 3 are fixed, the other 2 it runs through all the different combinations and averages them out. This example isn't too helpful, but it can be really nice if you want to reduce your set of variables down to 2 to 4 that you can actually plot on a heat map or a volume. To then plot this, it's pretty simple. You just have to do the same thing that we did before. Obviously, we're not plotting the window here. That's being grouped out of everything. So we're plotting the exit, the entry, and we'll throw in a slider level of symbol. I believe if you don't specify every column, so if I didn't specify the symbol here, I believe it just picks the first one, but I'm not too sure about that. There we go, here's our heat map for the different entry and exit points, averaged out across our RSI and moving average windows. Maybe this graph is helpful, maybe it's not, but that's just the technique that you can use to reduce down data into something that is plottable. Just for completeness here, I'll show you how to do the same sort of thing with volumes. So I'll get rid of this group by here. And since the MA window doesn't seem to do anything anyway, I'll just comment that out and it'll just use the default value that we specified earlier. And we'll create a volume out of the remaining 3 parameters here, plus 1 parameter for the symbol. That's going to be the slider level. Now, all you have to do, dead simple, you just go over here and you replace this with a volume. So vbt.volume, and you'll also want to provide a Z level, obviously being the height. So what variables do we have here? We have the RSI window, the entry, the exit. Okay, so it's going to be comb RSI level, entry, and exit, with the symbol serving as a slider level. And if I just run this, we should get a very nice little volume that we can zoom around and have a look and see which values look good. Apparently I misspelled our parameter here. It should be comb RSI window. Here we are, we have our nice little volume here. We can hover over the different points on the cube to get an idea of which sort of parameters are doing well. And we can get a general sense just by looking at the colors of the thing. To be honest, I tend to prefer the heat maps to cubes. The cube is relatively difficult to display the amount of information. But if you really need something to be in 3 dimensions, you need to look at 4 different variables. This is the way to do it. As usual, we can use our slider here to go between ETH and Bitcoin. It's generally useful just for noting that, for example, in our made-up strategy that we have here, lower values of entry are nearly always outperforming the higher values of entry. So that's pretty much everything you need to know about how to optimize your indicators once you've made them, how to test out a variety of different variables using Numpy. You can do this as many times as you like, or as much RAM as you have available. If you do find yourself running out of RAM, or it's going to take hours and hours or days and days to compute your backtest, you'll want to stick around for the next section, because that's when I'm going to be talking about optimization techniques. So we're going to be using things in order to vastly improve the speed of your backtests by as much as 10 to 100x. And I'll also teach you how to split up your backtest into chunks. That way you don't completely run out of RAM when doing your portfolio simulation. So I'll see you there. In this section, I'm going to go through some different methods of optimizing your backtesting scripts with Vectorbt, both in terms of speeding up how quickly the calculations go, as well as trying to reduce the memory footprint when that becomes a problem. Given that we've just been through the parameter optimization section, it can be very tempting to do millions of different combinations of parameters and completely max out your CPU and run out of RAM and your kernel dies and it's a bad time. So I'll be giving you some tips on how to avoid that as well. And so we'll start off with a discussion of how we can make our backtests faster conceptually. And in essence, it comes down to the choice of library that you use and how high level it is. So for example, Pandas is really easy to use. It's got some really nice functions that will let you aggregate things, bucket your candles, apply moving averages, etc., etc. The problem is that because of all that nice stuff, Pandas can be a little bit slow. That's why by default in any Vectorbt backtesting script, if you print out what gets passed to your indicator, it's actually a Numpy array. And so Numpy is a much lower level mathematical library. It doesn't give you all the bells and whistles that Pandas does, but it's also a lot faster and a lot more optimized, mostly because a lot of the code for it is pre-compiled C code. So essentially, the instructions are already there for the computer written in machine code, whereas when the Python interpreter looks at regular Python code, it has to figure out what's happening on the fly, whereas if it's pre-compiled, it just executes the instructions, makes it an awful lot quicker. So in general, if you want speed, you want to be using something lower level. Now, thankfully, there are people out there who've written libraries for us in these lower level languages. So talib is a very popular example. This is the Python package here, which you can find on GitHub and install with pip. And it's based on this talib here, so these talib packages. From what I recall, these are written in assembly, basically, which gives you the best performance, but we could integrate that library in Python with the talib package and get that same speed in a much easier to work with language like Python. There's also something called Number, which you may have come across before. And what Number does is it lets you take a subset of Python and Numpy code. So it works for most mathematical operations and a good chunk of the Numpy functions. And you can call the Number just-in-time compiler here as a decorator above your function. And what it will do is it will translate the Python code that you've written in that function into machine code that's ready to be executed. This can have a massive impact on performance, maybe like a 10 to 100x speed up, depending on how optimized your code was before, especially if you're doing lots of looping and that kind of thing. So I think I've explained the approach here of how we make things faster. Let's dig into an example so that we can see this in action. To speed things up a little bit here, I'm going to go grab an example from the parameter optimization section. So this is the file that we were working with there, where we had our custom indicator here, and we did lots of broadcasting and tried to make this indicator as complicated as possible, essentially. So I'm just going to take all of this and I'll copy it into our new folder here. So if I pull over this terminal and I'll make another tutorial.py and just paste it all in. You can use basically any indicator that you like here. You don't have to use the exact same one that I have, just as long as it's being made with the indicator factory and it has roughly the same structure, you should be able to easily follow along with what I'm doing here. So I'll get rid of this plotting section. We don't really need to look at that. And we'll remind ourselves what exactly this looks like. So by the looks of things, we have 4 different parameters here: entry, exits, and the windows for the 2 different indicators. We take the 1 minute data for each asset. We roll that up into 5 minutes, and we compare the 5 minute RSI with the 1 minute moving average by the looks of things. Now, we were forced to use a Pandas function here. If you remember, we're using rsi.align, where RSI is a Pandas series. And that is going to make the indicator quite slow here. And there's not an awful lot you can do to avoid it, unless you want to write your own function that essentially does this, but in Numpy or with regular Python code that you can apply the Numpy just-in-time compiler decorator to. So I'm just going to simplify this for now, just to make our lives a little bit easier. And we'll just stick with a regular old RSI, entry, and exit. So we'll get rid of that, and we'll use the 5 minute here. We'll get rid of the align. We'll get rid of this, get rid of this. We'll get rid of the moving average. And we'll set up something like this. So the RSI is greater than the exit, then we sell. If it's less than the entry, then we buy. Otherwise, it remains the same. And then, of course, we'll have to adjust our parameters here. So we're not giving it a moving average window. Get rid of that. We can also get rid of this keep PD equals true here, because this should be able to take a Numpy array. We don't have to keep things in Pandas format anymore. And we can also get rid of that. So let's just run this and convince ourselves that it works after we've made those modifications. So that looks like it's doing something at least. It's computing our backtest, which is great. And I'll also further modify the code here to just store a copy of this Bitcoin price here. Well, it's actually Bitcoin and ETH price on our local device, just so that we can accurately compare benchmarks when we do some optimization. And we don't have to concern ourselves with differences in latencies in getting data from Wi-Finance. We should just be able to do that with btc_price.to_CSV. We'll give it a name, call it data.csv, and that should be good. It should create a file in that folder. If we go back to our optimization here, there we go. We can see we've got data.csv. Let's have a look at that. So it's just a regular Pandas data frame here that you're normally used to. Let's go ahead and load it up. So instead of getting data from Wi-Finance, we can get it from this CSV. It's going to be equal to pd.read_csv, data.csv, and then all the normal stuff that we have to do. So we'll have to convert this to date time and make sure it's the index in order to make it exactly the same as what we had before. So that should be fairly simple. Just do BTC underscore price, date time is equal to pd.to underscore date time, BTC underscore price, date time, and then BTC underscore price dot set underscore index, date time in place equals true. Okay, that should be us set. I'll go ahead and print it out just so that we can check it's working. Although I guess our backtest will fail if I've got it wrong here. So if you print out the original Y-Finance data, it'll more than likely look exactly like this, which is it's good. That means everything is looking great. And we can more reliably compare our backtesting results here. So let's go ahead and just crank up the amount of backtesting that we do here. I want it to be really obvious, the difference in speed. So we'll double the amount of entry and exit points. That will more than likely quadruple the amount of computational time. And I'll make a note of how long it takes so that we can look at the speed up that we see and how well it's doing. By my reckoning, that took about 15 seconds from the point in time where I clicked the go button. Not too bad, but you can imagine if we had even more parameters. Let's say we had 6 different parameters and we also wanted to go one by one. It could get a real mess and take a long time. So let's use some of those concepts that we thought about earlier to optimize this. And then you can take those concepts from this simple example into whatever indicator you happen to be optimizing. So what I'm going to do is I'm going to replace this function here with a talib function. The regular old vbt.rsi.run, it works okay, but talib is going to be much, much faster for us. And as I mentioned before, you can install that from the GitHub package. It's just going to be pip install ta-lib. Now, it might fail if you don't have the underlying package installed. So you'll want to go to talib.org and make sure that you've got everything installed. There are also some instructions here on the GitHub. So if you go down here, it gives you Windows, Linux, and Mac installation instructions if you get a bit stuck. Do make sure that you've got those underlying libraries installed, otherwise talib won't work for you. So we've got talib. Let's go ahead and replace this function here. So we'll have RSI is equal to talib.rsi. And then we just pass in close and window. If you want to find help on a particular talib indicator, you can just go into a shell. So you can do Python 3 or Python, whatever it happens to be on your system. You can import talib. And then you can just do help talib dot whatever your function is, so RSI in my case. And it gives you the inputs that you need and then the time period and tells you what it returns. So it returns a real number, it takes in a real number, and it takes the time period with default value 14. Pretty standard stuff for the RSI, but things can get crazy for the other indicators. So let's head back to our file here and run it. We'll more than likely get an error here, but I'll show you how to combat it. That's not the error I was expecting. It looks like I didn't name my variable right, as usual, RSI window. So typically when you use raw talib functions, you're going to get this message here that says input array has wrong dimensions. And it becomes obvious what's gone wrong here when you print out the value of close here. So if we scroll up through this error, you can see that this array here is a two-dimensional array, with one side being the Bitcoin price, the other side being the Ethereum price, and we've just got pairs of entries all the way down. talib unfortunately can't read this format naturally. It just takes in an array and it returns an array. But there's a helpful option in Vectorbt here that we can use. So if you remember, we used keep_pd before. This is very similar. We're just going to use 2_2d, and that's going to be set to false. And so now it should only use a singular dimension. Let's go back and have a look and see what the matter is. Now it seems that even though I've specified not to go two-dimensional, it's still doing it. This is more than likely because we've got two different data sets here. We've got Bitcoin and Ethereum. Let's just try narrowing it down to one of them, and then I'm fairly confident that this approach will work. So if we narrow this down to say BTC_price is equal to BTC_price, and we'll just select BTC USD. And we'll print it out just so we can see what's happening. So now we see that our 2_2d actually worked, and it's printed out all the different combinations here, but we can scroll up a second, and you can see it's actually just printing out regular arrays here, like talib actually wants to consume. So that's great if you've just got a single symbol that you want to backtest against, or you can loop through different symbols. If it's important for you to get this working with multiple assets simultaneously, or if you're, say, simulating different windows, you can use the wrapper function that Vectorbt provides to wrap talib functions natively. So you can essentially just define a new function up here, call it RSI in our case, and that's just going to be vbt.indicatorFactory, and then .from_talib, and then the name of your indicator is going to be RSI in my case here. And instead of using the talib directly here, we can simply call our function RSI.run, much like we would any other built-in VBT function, except that it's now using the talib library, so hopefully things should go a little bit quicker. As usual with the VBT, you have to actually call dot and then the outcome here in order to extract the actual values of the indicator. Everything should run fine here if I press go. And again, if I remove the line that specifies Bitcoin here, it should still work, despite the fact we've now got two different assets. So that's the first step of our optimization here. Another step that we can do, although it's questionable how much of a speed up this will give us, is to convert this into number. In particular, these two lines here, the Numpy lines. So I can do something like, I can define a function, and I'll call it produce_signal. And it'll take in a few different things. It'll take in the RSI, the entry, and the exit. And it'll just do this basically. I will take the trend and return it. And then I can just go over here and return produce signal. We'll take in the RSI, the entry, and the exit. So all I've done there is just rearrange the lines around. Why did I do that? Well, it's because we can apply the Numpy just-in-time compiler on here. So you'll have to go ahead and install Numpy. I think it might already be installed if you have Vectorbt installed. Let's just check. Yep, it looks like it's already installed. So we can do from Numpy import ngit. So Numpy just-in-time compiler. And we can call that over here as a decorator, so ngit. And that will convert this function into machine code. It will compile it. And that way, when we run it in the future, it'll be a lot quicker. It might not provide a tremendous speed up here for this function, but you can imagine if we had some crazy sorting function where we were doing things to the RSI value in order to actually return our trend function, it'd be a lot more useful. Number works on a good proportion of Numpy and Python functions. So generally, if you're programming something in raw Python or in Numpy, you can speed it up with Number. So let's give this a run. Yes, it appears I tried to import from Numpy rather than Number. Easy mistake to make. And a classic spelling mistake down here. Produce signal. You want to make sure to convert this to Numpy here so that it can actually ingest it. I believe this will output a data frame, which we don't want, so 2_Numpy will work for us. I don't believe we need this 2_2d equals false anymore either. Since we're using regular VBT functions, it should work normally. So I'm going to crank up the amount of combinations here and do some comparisons with our original, just to see how much of a speed up one can realistically expect. So I'll crank this up to a step of 1. So we'll get many, many more combinations here, and I'll do some experiments. So I did some comparisons here between the version that we had originally here, or rather just the simpler version using vbt.rsi.run, compared with this version, which uses the talib RSI function, as well as using Number for the signal creation. In the end, we ended up with about a 30% difference between the two. So this one's about 30% quicker, which wasn't actually as dramatic as I expected. Although I guess this function is pretty optimized already. We're already using Numpy functions for the signal generation and just the one indicator. Still, 30% is nothing to sneeze at. And the more complicated your indicator is, the further that you get away from just running one simple indicator, the larger an impact this is going to have. Using these principles of compiling code where you can and running optimized versions of indicators, I've personally got speedups of 5 to 10x through just little refactorings like this. So it's well worth learning how to do if you're going to be sticking around in the Vectorbt ecosystem for a while. If you go onto the vectorbt.pro website, there's a good example here. It's called Superfast Supertrend, and it goes through these sort of concepts about what libraries you use. So do you use Pandas, which is the slowest option but easiest to use generally? Or do you want to use Numpy and Number, which is very quick, but slightly more stressful to use? Or Numpy plus Number plus talib, which is incredibly, incredibly quick. This can provide some good further reading if you're looking for a slightly more complicated example that really shows the power of these different libraries. As far as speeding up the computation goes, that's about as far as I can take you right now. The next thing I'd like to briefly look at here is how we can optimize our memory usage. So if you're going to be running lots of backtests, maybe like 1 million different backtests, which is not uncommon really, then you're going to be using a lot of RAM. And if you don't have a lot of RAM on your machine, you're going to have a really, really rough time of things. And one method of dealing with this is to split your computation up into different sections and allow Python's garbage collection to free up the RAM as it goes. So if we open up our file here, we go down to the bottom here, and essentially this section from indicator.run all the way through to calculating the portfolio here, and even the returns, we can segment the backtests and split them up into different batches. One easy way of doing that is to run a for loop over our choice of indicators here. So we can run one batch for each RSI window effectively, and then allow Python to free up the RAM in between calculations, and then we calculate the next batch, so on and so forth. So if I say RSI underscore windows is equal to that, and then we'll indent this whole thing, and we'll just do for window in RSI underscore windows. And instead of providing this, we'll give it our window. So you just take one parameter and then iterate over it and do a separate batch of backtesting for each one of them. So for a window value of 10, this is going to do a full backtest with all the possible other combinations of variables, and it will also calculate our returns. Now at the minute that's not going to be too useful because we're not doing anything with the returns, but we can gather them all together. So if I create like a master returns, and that's going to be an empty list, and then I'll just append the total return every time we calculate it. So we'll do master returns.append. And then at the bottom here, I can print out the master returns. So we can see here in our output the results of each backtest. So this is the backtest with the window equal to 39. This is the backtest with it 38, 37, so on and so forth. All we need to do is combine these together, and it's as if we just calculated them in one big bunch. So I can go down here, I can just say returns is equal to pd.concat master returns. So the pd.concat is going to do what it sounds like, and it's going to concatenate all of those series together. And we'll end up at the end of it with one big return series, much like we would if we'd calculated them separately. But we have much less of a RAM profile because it's not having to store as many backtests or simulate them all at the same time. It does them in batches, which massively reduces the memory overhead. I just did a little test there, and in comparison, the version here that runs through all the windows only used about half the peak RAM as the version which doesn't bother with the looping here. This one used about 15% of my available RAM, which is about 2 gigabytes, and the other one used about 30%, which is about 4 gigabytes. You can, of course, repeat this concept and just do a for loop in a for loop here if things are getting particularly terrible. So, for example, you could iterate over this one, and you could call, entry is equal to this, and then do for entry in entries. Yeah, so if things are really terrible RAM wise, you can do something like this to try and ease the burden on your system as far as RAM consumption. Although it'll probably slow down the rate of calculation, but such is the price you pay for having a lower RAM overhead in your script. But at that point, things start getting a little bit squirrely, and you're not really leveraging the full power of Vectorbt. So generally, just easier to iterate over a single variable that you've pulled in here, and that should considerably reduce your RAM consumption and at least prevent your kernel from dying in the process. So that's all I've got for you in this optimization section. Basically, try to use lower level libraries if you really need that extra speed, like talib or just even Numpy or just regular Python, but use the just-in-time compiler to really speed things up. And then if you find yourself running out of RAM, which you might well do depending on the amount of backtests you're doing, try and iterate over a particular variable, or you could iterate through the different symbols. That would also be a perfectly valid approach. and then join everything together at the end to produce a returns list rather than trying to do it in all one go. And that should dramatically reduce the amount of RAM that you need without crashing the kernel. So I'll see you in the next section where we'll be talking about graphing and dashboarding in Vectorbt. In this section, I'll be covering the graphing functionalities of Vectorbt a little bit more in depth. So we'll be looking at how to plot our indicators and turn that into dashboards that we can use, as well as how to manipulate some of the basic settings of the plots themselves, like how wide they are, whether we use a light or dark theme, etc., etc. Now, Vectorbt uses Plotly as its main plotting engine. So if you were with me for the last section, you would have seen the heat map and the volume section, which are of course both borrowed from Plotly, but there's no reason we can't do any other kind of chart, like a scatter graph that we can add lines to, say, to indicate the different levels of our indicator. You can do anything that you would do in Plotly within the Vectorbt framework. Now, overall, as far as ease of use goes for dashboarding, I think Vectorbt still has a way to go. I would say that this is one of the weakest aspects of the package, in my opinion. But I'll also show you in this section how you can export the data from the backtest. So how you can export the trade data, and then you can plug that into any plotting engine you want. You can use Plotly, you can use Plotly Dash in order to construct your dashboard of different graphs that you can look at. You can even plug it into something like Power BI or even Excel, I guess. So if you have some kind of plotting utility that you're really familiar with, then by all means feel free to use that instead. The plotting functionality within Vectorbt outside of parameter optimization is still in early stages, I would say. So you can probably skip the rest of this section once I've shown you how to extract the trade and order data and go ahead and make your own charts. So without further ado, we'll dig into the code and we'll be specifically looking at scatter graphs in this section. We've already looked at heat maps and volumes, and towards the end, when we're evaluating our performance, doing our reality check, we'll be looking at maybe some box graphs to think about the distribution of our returns. So let's get going. So I've got here a very simple setup. It's very much like the Quickstart example we used at the beginning. I'm using a moving average instead. The reason being that we can plot that directly on top of a candlestick graph and it looks good. Because in this example, I'm just going to show just one graph for now, and then we'll build up to multiple graphs and dashboards and whatnot. So obviously the most basic plotting function we have in Plotly is just pf.plot.show. And what that produces is a basic dashboard with 3 different charts in it. So we've got the orders screen, we've got the P&L, and the cumulative returns. These are 3 built-in graphs which you can use in your own dashboards later on. We can also plot them out individually if we want, just by calling their associated function. So we'll comment out this plt.plot.show here. And let's go ahead and just plot the P&L on its own. So to do that, you take your PF, so that's your simulated portfolio, and you do pf.trades.plot_P and L, then .show. And of course, this just returns the P&L plot on its own. Can be quite useful if you're just after a particular one of these graphs. If you're wondering where I found out the name of the function that we called on the portfolio, you have to go back to the documentation here. And if you go into portfolio and base, then scroll all the way down. This is a really big document. you can get to all the different things that we can plot out here. So these are all the default built-in ones, at least most of them. So you can do things like plot trades, trade P&L, assets, cash flow, etc., etc. I'm not going to go through all of these, but I will show you a couple more just to see what they're like. But you can find them all there on the documentation. So we can do things like plotting the trades here. So instead of plotting the trade P&L, we just plot the trades. And that gives us a screen not unlike our orders screen from earlier, except we have these boxes here showing us which trades are profitable, which trades not profitable, etc., etc. We can also do the same thing with the orders. And of course, that just gives us our default order screen that we're used to, that we saw back here in this screen. Of course, you can plot cumulative returns. That'll be in here somewhere, cumulative returns there. So I hope you get the idea with this sort of thing. This is a dashboard composed of these individual built-in functions that you can call from the portfolio here. And there's, 10 or 20 different built-in ones, which should cover most of your basic use cases if you're just wanting to establish how well a portfolio performs, what its drawdowns are like, that kind of thing. But if we're not satisfied with these defaults here, we can also plot our own graphs. Now, as promised, you can also extract the orders here from the portfolio. So I believe if you do pf.orders like this, and you print them out, we actually just get an instance of the orders class here. So if you go back to the documentation, you go find orders here. So it's part of the portfolio documentation again. You can see we've got this class here called orders. That's what we've extracted here. Now, in order to get the records, we have to extract them here. You can see they're a part of the orders here. So we should just be able to grab those. If we grab the records array, I'm sure there's a nicer function hidden somewhere in the documentation for gathering these, but this is the best I've found at the minute. Now, the format that we get this in might look a bit intimidating at first, but hopefully there's a nice schema on here. So if you go again back up to orders field config, I'll split screen this so we can see what we're looking at. And the first column here is just the ID of the trade, so that makes sense. They're just increasing monotonically. So this is the 0th trade, the first trade, so on and so forth. The col here, I believe, refers to the column within your data table here. So I only have one column, one asset, so it's just going to be 0 the whole way down because it's trading the same asset. The IDX here, that is going to be the index of your data here. So how many bars in are we? So in this case, we're 321 bars in. It made this trade. Then the next column is just going to be the size. So how much of an asset did it buy? In our case, it looks like it bought 2.5 millibitcoin for a price of $39,530 each. This column is fees, as we can see, and then this is side. And then we can go down here and we can see the mapping. So buy is 0 and sell is 1. So that hopefully explains how this works here. This is the orders section. So you can, at any time, you can extract this data from Vectorbt, save this down in some kind of text file, and pull this into your favorite plotting utility. You're not bound to using Vectorbt. You can always come up with your own pipelines for extracting this data and then plugging it into Dash or Power BI or whatever you happen to like to use for plotting. Let's do the same thing with trades here just to show you how that works. So again, we can just print out pf.trades here, and we'll more than likely get an instance of the trades object here. But we can see it's got a records array parameter here that we can access. So I'll go grab that. And then we can just index our way into it here. So it looks like we're going to need a full screen in order to look at this. So again, a trip to the documentation will help us out in deciphering this. If you open up here, we go to trades. So you just type in trades, you'll find it here. Just in the portfolio section again. You basically just map these columns to these columns as we did for the orders. So if I wanted to find the return, it's the fourth from the end here. So 1, 2, 3, 4. This is the return for each one of these trades. If I want to find out what this number means here, well, it's the second from the end, so it's a status. And then we scroll down to see what the different statuses are. And we discover that 0 is open, 1 is closed. Makes sense, all of these are closed because of the way we set our trading up. So that's how you can extract both the orders and the trades from any backtest you want. And you can plug that into any plotting library that you like and do things your own way. For the rest of this section, I'm going to walk through some basic integrations that we have with Plotly here in Vectorbt to draw our own custom charts without leaving the comfort of this single Python file here. So I'll delete everything we've got so far in terms of plotting. We don't really need it. And we'll start off by just declaring a figure. So if you're familiar with Plotly, you'll be familiar with the concept of a figure. It's basically just a graph or one section of a chart. So I'll declare this to be BTC price, which is our price data that we're grabbing from yfinance here. And then we can just call .vbt.plot on it. You can do this with almost any object in Vectorbt. You can call .vbt.plot on it, and it will probably work. So if we try that, and then we just do fig.show, let's see what happens here. So obviously nothing particularly amazing here, but it's actually plotted out our data. It's sorted out the X and Y axis so they're appropriately scaled. Pretty good overall just for that one line of code. Let's go ahead and start building on that and making it a bit more interesting. One thing that we can do is we can add some keywords to pass to the base underlying Plotly function. So there's a parameter called trace quargs, and that's a dictionary. So I'm going to create a dictionary and I'll set the name just to show you. So the name is equal to price. So we saw in the graph that it automatically generated, it called it closed. Now that must be just the name of the series just buried inside the data frame somewhere and it extracted that. But if I set the name here to be price, it should instead give the name that I have given it here. So we can see the label here has changed to price, which is pretty cool. And you can do this with almost any parameter that Plotly takes. So let's try it with the color attribute and let's see if that works. So we can do something like color is equal to red. That should just be a built-in color that'll work for us. As you can see here, it didn't like that I gave it the property for color. Helpfully, it prints out everything that you need in terms of the different parameters that you can set. And if you get really lost, you can look through the Plotly documentation and just attempt to find the different things that you'll need to change the plot color. I went ahead and did that ahead of time. And if we come down here, we actually need to create a new dictionary within this dictionary called line. And that's going to be a dictionary. And in there, we set the color to be red. And then that will actually change the color of our line here. So we've gone through how to change the color, how to change the name here. I won't go through too many more of these parameters because this isn't a Plotly tutorial, it's a Vectorbt tutorial. So let's think about how we can add something extra to this graph. So we've just got the one line right now representing the price. That's a little bit boring. So what I'm going to do is I'm going to add the moving averages that we calculated earlier on top. So I'll just copy and paste this, and it's going to look quite similar. Just obviously instead of BTC price, we're going to plot the fast and the slow MA. All of this can stay relatively the same. Obviously, we'll want to change the name here. So slow MA. We can change the color if you want. I can change this to blue. One thing that you'll definitely want to include here is you'll want to set the figure. So you'll want to set the fig equal to fig. So this fig is the parameter name. This fig is the previous fig we've defined here. So you can think about this as we're just adding a new layer to the same figure. We're not defining a new figure from scratch. We're using the old one and we're like painting a new layer on top of it. That's a way to think about how we're doing this here in Plotly. So we've got that, and then we'll do the same thing with the slow MA. I just realized I put slow MA instead of fast there, and then we'll just give this another random color. It'll probably look hideous, but that's okay. It's going to be green, and then if I plot that, we should now have the moving averages plotted nicely on top of the price. Of course, we would do if we extracted the actual moving average values. So you may remember this from the earlier sections of the video, but this fast MA here it doesn't actually represent the underlying values. It's an object which we can call other functions on. It's not just directly the list of values. If you want to extract the list of values, you have to call .ma. And so we're actually plotting a data frame here, essentially. That's what MA represents. It should work now. So here we are. We have a slightly funky graph here. I can zoom in. We can see the values of our slow MA, our fast MA, and theoretically where our different points here should be, where we enter and exit different trades. Again, Vectorbt comes to the rescue here and provides a very nice function for plotting our entry and exit points on top of an existing graph. It looks very similar to the syntax that we've used so far. It's just fig is equal to, then you'll want to pick your signals dictionary here. So mine's just going to be entries or exits. So entries .vbt.signals.plot _ as _ and then entries or exits. So in this particular instance, I'm using entry markers. So entry markers. Then you'll want to provide your price data. So mine's going to be BTC price. And then as usual, we're going to provide the figure. So it paints on top of the old one here. So I'm going to copy and paste that and do the exact same thing here for the exits. So exits.vbt.signals, plot as exit markers here. And if we let that go, we should have a rather more funky looking plot with our different values on it. Doesn't show up amazingly well because of the red line here, so the entry markers are red, but if we zoom in a bit, we can see here that they're in the right location. So when the fast moving average goes below the slow moving average, we sell, and we buy on the inverse. We can see that that seems to be working for us. The entries and exits are in the right place. You can mess around with the color scheme to get this looking reasonable. This, I would suggest, is a nice way of just visually validating your strategies. Oftentimes, you can write something up in code and just look at the text details of the backtest and not be able to figure out whether it's actually following the behavior that you originally designed it for, or whether it's doing something completely different. This can be a nice way of just plotting your indicators on the graph and getting an idea where your entries and exits are, and whether it's behaving as expected, basically. A couple more things I'll show you here before we finish up with this particular example. One of those is how we can set the theme of the graph. So there are 3 built-in themes that you can use without doing anything fancy in Plotly itself, messing around with the trace parameters there. And you can alter those by accessing vbt.settings.set_theme. And then there are 3 different ones you can choose. So light is the default theme, so that's the one that's already in place. You have Seaborn, which uses the Seaborn library. You might be familiar with it if you've used matplotlib before. That also has a Seaborn theme. And we also have a dark theme. So I'll show you the dark theme just to see what that looks like. Obviously, this is just personal preference. You can have your graph to be however you want it to be. We can also change the sizes of the graph. So we can do that again by looking inside the settings here. So you can do vbt.settings, and then this is a dictionary, so we're going to access the plotting, then layout, then width or height, depending on what you want to change. And then you set this to a number of pixels, so I'm going to set this to be fairly large. I'll set it to 1200, and I'll do a similar sort of thing with the height here. So I'll set that to be 600. And that should give us a decent sized graph. I'll also show you what Seaborn looks like here. The default size for plots is very small. This is a bit more civilized, obviously. And if you have some crazy 4K monitor, feel free to crank this up so you can zoom in and see the exact price action that's occurring with your buys and sells. So that's the basics of how you can make single plot charts in Plotly. And with that under our belts, we'll be able to tackle slightly more complicated issue of doing multiple graphs on a single dashboard. So I'll exit out of all of these different graphs we've got going on here. And we'll head back on over to our file. I'll comment out all of these different figures that we've made for now. We don't really need them. And to begin with, I'll just show you how we can mess around with the regular old pf.plot function in order to draw things that are slightly more interesting. The easiest way to make multiple plots here is we just override the subplots object here that's part of our plotting. So that takes a list, and if you want to just use some combination of the default plots that come with Vectorbt, you can just reference them by name. So for example, I can say orders here, I can say trade underscore P&L, and I can say cumulative returns. And that will give us the default layout actually that you get in a normal Vectorbt layout. Let's go over here and see if we can pick some other ones as well that we might want. So I'll grab, say, drawdown here, and we'll see what that looks like. So it should be drawdowns. And then I'll close on out this list. And that should give us what we want here. Make sure you've got your fig.show at the end, and this is actually declared as fig. So pf.plot is going to produce a regular old Plotly figure, and then we do fig.show as we would in any other Plotly project. It's orders, not order. And there we go. I forgot that I'd supersized the size here, but we can see we've got our 3 different charts, or 4 rather, in exactly the order that we specified. And you can do this with any of those built-in charts that I showed you earlier. You might have to mess around to get the exact name that Vectorbt refers to it as, but you can put them in there and it will bring them up in the order that you specify, which is pretty handy. Now, of course, we might want to create our own charts and put those on this dashboard. So how do we go about doing that? Well, according to the documentation, there are 2 ways of doing it, or at least 2 that I could find. And one of them is to create a plotting function that Vectorbt can load. And the other is to just define an empty space here in our subplot. So we create a sort of a blank slate in here, and then we override it later with a figure. The second one is what I prefer for just getting something quickly up and running if we want a multiple dashboard type thing, just running with Plotly. Again, if you want something super complicated, you might want to just run straight Plotly rather than trying to interface it through Vectorbt, because things can get a little bit complicated. But regardless, let's soldier on here. And so in this list here of our different plot names, I'll create a tuple here. So the tuple is going to be a name, so I'm going to call mine price, and then a dictionary. Now the dictionary, we can have a few different things in here. So we can have a title, that's going to be equal to price. And we can set things like some keyword arguments for the X and Y axis if you wanted to. So you can do things like Y axis keywords is equal to another dictionary. Title is equal to price. We'll really make sure it knows about the title. And I think that should do it in terms of just a basic override here. So if we just run this, I think we'll just get a empty slot. Let's see what happens. So we've created a sort of placeholder here at the beginning. It's called price. There's nothing in it at all. There's no plot, no figure. We need to go ahead and define that. All we've done is told Vectorbt that there's going to be something there, and it shouldn't place any of the other plots in that section. So let's go ahead and fill in that particular plot. And we can do this after the figure here. So after we've defined this figure, we'll go ahead and add the scatter plot on top of that particular section. So the way you do that is you create some sort of variable. I'm going to call mine scatter, and we'll create that as an instance of the Vectorbt scatter function. So presumably you can put anything in here. You could put heat maps, you can put volumes, anything that you can draw with Vectorbt, you can put in here pretty easily. I'm just going to use scatters because that's what we've been using so far. So vbt.plotting.scatter. Now we need to provide the data. So the data is just going to be the BTC price, fairly straightforward. Provide the X labels, and it's just going to get the BTC price.index. Then you want to provide the name of the trace. So that's what will appear in the top right hand corner that we can click on and off as we so choose. So trace names is equal to price. And then importantly, we need to add some additional keyword arguments here. So that's going to be add underscore trace underscore quarks. So this will again get passed in to the underlying Plotly library. So the underlying function that's being called here by Vectorbt, that's where these keyword arguments are getting evaluated. And the ones that you really need to worry about are just specifying which row and column of the dashboard the plot you want this to go in is. So in our case, it's row 1 and column 1. You can have multiple columns, and I'll show you how to do that in a second, but for now, let's just figure out how to do a single column. And then, as before, you'll want to specify figure is equal to figure. And that'll make sure it's drawn on top of our previous figure. Now, all being well, this should work, and it will give us a nice graph. Of course, this keyword here is col rather than column. And there you go. We can see that we've got the price here directly overlaid on this section. We've got the trace properly labeled up there. We can click it on and off. And so this works quite well, really. If you want to go ahead and mess around like we did last time with the color and that kind of thing, you can do the exact same thing here. So I'm just going to borrow this section here where we define those quarks. I think those 2 brackets are necessary. Yep. And I'll get rid of the name here. We don't really need that. But if I do this, you'll see that we can change the color like we did before. So you can set that to be whatever you want, and you can modify this again exactly as you would any other plotly diagram, because that's literally all it is. You can even add scatters on top of each other on that same section. Just make sure that you specify the rows here. So we could have a whole another scatter here, call it scatter 2. And that could be plotting the BTC price, I don't know, +5. And then you'd have 2 traces in that same section there. So that's cool and all. We have our scatter plot here of the price. Let's add an indicator on a separate dashboard here. So we've got the price, the orders, the P&L, the cumulative returns, the drawdowns. What I want is to again plot our moving averages on top of here. So the way we do that is exactly the same way we did it before, except we're using plt.scatter here. And instead of the BTC price being our data, it's just going to be the fast or the slow MA. So I'll just call this scatter 2, or maybe fast MA scatter. I don't think it really matters. We're not using this variable anyway. So the data is going to be the fast_ma.ma. And then this is going to be the exact same thing. It's just going to be fast_ma.ma.index. And then we want to change the name here to be fast_ma. And we'll change the color to be green. Do the exact same thing, copy it again. And we'll instead plot the slow moving average. Just spotted a spelling error there. Fast MA. And then this will be slow MA. And the color will be blue. So let's plot this and see what kind of trouble we can get ourselves into. There we go. You can see it's worked exactly the same as before, really. We've got our moving averages on top of our price. Now you can repeat this as many times as you want. So we just used one placeholder here, but there's no reason you couldn't copy and paste this here and just do the exact same thing. And obviously, instead of specifying row 1, column 1, you'd want to specify row 1 or row 2, column 1 rather. So if I go over here, I can probably do something like this, where I plot the moving averages in their own plot below the price. It's going to look a bit weird, but it serves my point of showing you that you can have the 2 graphs under each other, and you can define as many of these as you like. That doesn't matter too much. So you can see here we've got the moving averages on their own, and then over here we've got the price. We can also go ahead and plot the entries and exits exactly the same as before. All you have to do is make sure to include this additional trace keywords argument here. And you can use any of these functions. You don't have to necessarily use the scatter function. So for example, we can go back to the old form here. And if I just actually copy and paste this one, put it over here, and we'll just say entries plots, yada yada yada, plot as entry markers. We use the BTC price, and then we'll grab the row and the column that we want to plot it on. So since this is being plotted on the graph with only the moving averages, I'll use the moving averages to say where it should be. So it's going to be the slow MA, slow_ma.ma. I'll do the same thing for exits here so that you can see what's happening. to be exits.plot as exit markers. I think the colors will mess with it a little bit just because we're using the green as the other one, but you'll see what's happening. So there we go. If we scroll down here, we can see our entry and exit markers as well as our indicators. And this is all incorporated within our dashboard here. So that's pretty cool in my opinion. And since this is just a regular plotly graph, we can also do interesting things like we can add lines to the figure. So let's continue our theme of editing this second graph here and make it look a bit weird. We'll add a horizontal line across, which it doesn't really make sense, but I'll just show you for the sake of thinking about the fact that this is just regular plotly object. We can do whatever we want to it. So we can do fig.add_h_line. Then we set a y value. So let's have a look at our graph, see what would be appropriate y value. Set 38,000. 38,000. We'll set the line color. So the line color, I'll just set that to be FFF, because I can never remember any hexadecimal colors. Then you want to select the row and the column as before. So the row is equal to 2, the column is equal to 1. And then you also want to give it a line width. So I'm just going to say 20 to make sure we can see it. I'm sure this is going to look absolutely hideous, but I'm just trying to prove a point that we can do whatever we want to these plots. There we go. You can see apparently FFF is white. So it's drawn a white line here. Obviously that blends in with the background at 38,000. You can obviously do this to maybe show resistance points, or maybe this is a threshold for your indicator. Just a few ideas. You can also do exactly the same things you would do in Plotly, where you can draw rectangles or other shapes. You can annotate. You can do a myriad of other things that would take all day to explain. So I'll leave that with you to explore the Plotly documentation. One final thing I will show you, as I promised earlier, is how we can add different columns into the equation here. All we have to do in order to do that is we just have to add a extra quarks argument here. So pf.plot is going to be using the plotly subplot function, and we can provide quarks to that. So we can set the make underscore subplots underscore quarks dictionary here. Now you'll have to go look at plotly subplots function in order to figure out all the different quarks we can set. But the most important ones are the rows and the columns here. So we can set rows, we can set that equal to whatever we want. We can set that equal to 10. And we'll set the columns equal to 2. So we should now theoretically have a 2 by 10 system. Now if I run this, it will almost certainly get real messed up because of the way we've got things ordered here in the subplots list. So it is showing the two different columns here of the dashboard, but you can't really tell here, but it has actually covered up the orders graph here. And the reason for that is that if we go back, Plotly is going to plot these left to right and then down. So the first one is going to occupy the top left spot. The second one is going to occupy one to the right of the top left spot. So that's why this is blank here, because this actually represents the top right in the current configuration. And then it continues its merry way down the list. So it goes here, 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 here. That's how the order of things works. So basically all we need to do to fix this is we just need to adjust our row and column numbers when defining that second graph to be in its correct place. So the graph now is in the top right. So that's going to be a column of 2 and a row of 1 basically. So we just need to change these around and everything should fix itself. There we can see the graph is now in its proper place. So I hope this section was useful for you. If you need something more specific, again, you can look through the Plotly documentation to find any specific keyword arguments or functions that you need, or you can just take Vectorbt out of the equation, extract your order data, and build your plots on that using whatever tool you happen to be more comfortable with. But that's the basics of the things that you can do in Vectorbt. You can of course replace these scatter functions with any of the other different plots that Vectorbt offers, of which there are a fair few, heat maps, histograms, gauges, box charts, bar charts, so on and so forth. But I'll leave that as an exercise to the reader as we continue into our next section on different order types. In this section, we'll be doing a quick rundown of the different kinds of orders that we can submit using our portfolio.from_signals function. So far, we've just been doing a very simple long strategy where we buy when there's a long signal, and then at some point, depending on the value of our indicator, we close that long position. But Vectorbt also supports a variety of other order types that we can do. We can also enter and exit short positions, and we can also add in different kinds of stops. So we can add a stop loss, for example. Say if you wanted to cut a position if it lost more than 5%, you can also convert that to a trailing stop loss. So it automatically follows the trade, and if at any point it falls, say 5% from the peak, it will cut that off. We can also include things like take profits. So you could again add something in that says, regardless of what happens, regardless of our entry and exit signals, if we reach a 10% profit, then we want to just immediately exit that position. And this also applies to both short and long positions. So that's what we're going to get into in this section. It's surprisingly easy once we've already got all of the indicator development out of the way, because there's already such nice, easy functionality built into Vectorbt that allows us to do this kind of thing with our orders. So let's go ahead and get started and look at a couple of examples to see how it all works. I'll start off here by directing you to the place in the documentation where you can find out basically everything I'm going to show you here and an awful lot more. You'll want to go to the vectorbt.dev, which is the documentation website, and then go into the API documentation, portfolio, then base, and then finally we find our from signals function. There's also a from orders function that you can use if you're feeling adventurous, but from signals is much simpler, at least I've found. And you can see in here all the different parameters that we can provide. So far, all we've done is give it the closing price, the entries, and the exits. But you can see here there's also short entries and short exits. Those behave exactly as you might expect. They're essentially just the inverse of the entries and exits here, and you can use that to generate short positions, which we'll do in a second. There's a few other miscellaneous settings here, like fees and slippage. We'll deal with that in the next section when we talk about how to make our backtesting more realistic. But if we scroll further down here, we can find things like our stop loss here. Then we can find whether we want it to be trailing or not, our take profit stop loss, as well as a few more niche options here to do with stop losses. So we'll go ahead and just start with a copy of our Quickstart that we made right at the beginning of this video. So I'll make sure that we're in the relevant environment here. So I'll do source Quickstart vnv/bin/activates. Then we can get back to our order types here. And you'll see I've just got a very simple copy of our Quickstart. So all it does is simple RSI, gonna enter when the RSI crosses below 30 and exit when it crosses above 70. Simple enough. I'll just run it here so you can see what's happening. Grabs the last 3 days or so of daily data from Finance, and then creates a bunch of different returns for our assets here. To make it a little bit simpler, I'll just change it so that it only grabs Bitcoin data, and let's not include these 2 different windows. Although everything I'm about to show you in this section works perfectly well with everything else I've shown you so far, so you can combine this with your custom indicators, no problem. You can add in different windows as well. Pretty much everything we've done so far should work seamlessly with these different types of orders. Let's go ahead and plot the results out here. So maybe I'll turn it down to just 1 day so that we can more easily look at the different trades. And I'll uncomment this plotting function here. Apparently I missed out a bracket when I was deleting. So here we are, nothing too exciting. It takes a long position and then it closes the long position, etc., etc. It just repeats this until we get to the end here. So that's all boring and normal. Let's add something in that makes it a bit more interesting. So we can see that we're taking some relatively large losses here, at least compared to all the other trades. These seem to be rather poor indeed. So maybe we could add something of a stop loss in here at, say, minus 0.5%. And as I alluded to before, Vectorbt makes this very simple indeed. So if I go down here to the different parameters, I'll neaten them up a little bit just so that we can add some extra ones in. And the option that you want to add a stop loss in is SL_stop. Again, it can be found on that documentation page I was showing you earlier. And you just set it to a decimal value. So I'm going to select 0.005, which as a percent would be 0.5%. It's worth noting that you can also make this into an array. So if we check the documentation and we go find it, we go to stop loss, you can see array-like or float, or rather array-like of float, and it will broadcast that. So we're just going to give a single float value, but it will interpret that as an array of this particular float value. What this means is that you can provide a different stop loss value, so a different amount of stop loss for each individual bar. So you could have some other indicator, let's say it's based on the volume, and that could determine how cautious that you want to be with your stop loss. You can do all sorts of really interesting things here. You could have an indicator that spits out a value for every single bar, paste that into here instead of the float value that we're giving it. And now you have more of a dynamic stop loss where on every single bar has its own particular unique value depending on the variable that you set. Just a really cool feature of Vectorbt and how customizable it is. So hopefully we should get to see this stop loss at work here. It should trigger on those trades that were losing more than 1%. You can see now the cap is like minus 0.6%. It's not perfectly 0.5%, mainly because of the resolution of our data. This is not tick data, it's just going to execute it on the next bar that is below 0.5%. And as we can see with most of them, that tends to accumulate around the maybe 0.6% region. But nonetheless, we can see that the stop loss here has saved us from some rather awkward situations. It cut out that bit of loss there, although it did cause us to take an even bigger loss on this section because of the way of our indicators. But the main thing is that it does seem to have actually functioned. It's equally as easy to add in something like a take profit region. Now, our strategy here is not amazingly profitable, so I'm going to add in a very, very small take profit, and just so we can see that it works. So if I go over here and I add in take profit underscore stop, and let's set that to something really small like 0.01%, or rather 0.1%, I mean, so 0.001 as a decimal. If we run that, we should see that most of our profits are going to be centered around that 0.001 line. In our case, this tends to make this strategy not perform too well because we're getting lots of losses of about 0.5, whereas all our gains are capped at 0.1. But nonetheless, we can see that it's all working. In order to convert our stop loss there to a trailing stop loss, pretty easy. All you have to do is add a SL trail equals true. And I'm pretty sure you can even do that as an array. So if I go back, SL trail, yep, you can again provide that as a array. So you could have it dynamically in some places, have the stop loss be trailing, and in some places not. Equally the same with the take profit. I'll run this and see if we can notice any difference between the two graphs, although I don't expect it to be overly noticeable. If we flick backwards and forwards here, yeah, the trailing stop doesn't seem to have done anything in this case, but maybe on a different strategy it would be more noticeable. Let's dig into some maybe more advanced features in here. So we can go back again to the documentation. You can see here that you can actually provide the stop prices yourself. You can see here there are lots of different configuration options for your stop losses. So over here, you can choose what Vectorbt actually looks at for the stop price. So you can include slippage in there, or you can just look at the straight asset valuation. A pretty niche option, so I'm just going to continue going forward here. One that might be of interest to you though is this upon stop exit option here. So if we have a look at those options, you can see that we have 4 different options here. So we have close, close reduce, reverse, and reverse reduce. The main ones you want to focus on here are just close and reduce. So close is the default behavior. That is when we reach a stop loss, we close out our position, whether that be short or long. So if we bought 1 Bitcoin and we reach our take profit, then we sell that 1 Bitcoin. One pretty cool thing that you can do in Vectorbt though is that you can reverse your signal. So say if the trade's going against us and we reach our stop loss, we might predict that that trend is going to continue. It's going to be a negative trend. The trade's going to go against us. So we can reverse our trade. So if we had 1 Bitcoin and the trade went against us, we could sell 2 Bitcoin when we hit our stop loss and effectively go short 1 Bitcoin and close out the initial trade, and hoping to make a profit on that short trade now that the trend in the market has changed. I'll add that to our Quickstart option here, and it might make a bit more sense. Now, for these options here, so you can see some of them are enums. So if you click on them, you end up in this enums section here. That just means there's a mapping here of the different options to numbers. So if you wanted to, you could provide an array with different numbers in them, the same length as the bars, although it does appear to broadcast, so you could give it 1 value as well. Alternatively, you can actually grab the name. That's what I prefer to do. In order to grab these by their name here, all you have to do is index into VBT itself here. So if I go back, we can grab that with upon underscore stop underscore exit. So that's the parameter name. If we go back over here, you can see that's the parameter name. And then to get the value of the enum that we want, all you have to do is vbt.portfolio.enums and then .stop exit mode. I'm getting that from the title here, so this section. And then pick the one that you want. So I'm going to pick reverse here just to make things a bit more exciting, and maybe we can see its effects on the graph of the trades. So reverse, And that should work, hopefully, if I add a comma there. And let it run. Our returns don't seem to be doing so great here, but let's see if it actually went ahead and executed our strategy. So we're looking for regions where a stop has been hit, basically. It's worth noting that the reverse here also applies when we take a profit. So if we go back to the chart, we can see that I imagine this hit our take profit here. And so if we look at these two trades, this one has a size of 0.0025, whereas this one has a size of 0.005, so it's doubled. So the reverse signal applies for all kinds of stops. So when our take profit signaled here, which is a form of stop, we reversed our position and we actually went short. So we're now short for something like 0.002 Bitcoin. Then, since we're now short, we buy down here, and that reverses the position yet again. So we were short about 0.002, and now we're long that same amount. And so on and on this goes here. It's pretty cool that we could add that in there just by adding one line and selecting one option here in the portfolio from signals function. I guess we can now take a little look at how to implement shorting. It's actually pretty easy once you've got the hang of using everything else in Vectorbt. All you have to do is set the short entries and short exits here. So if I go in here, and let's say we want this to be essentially a short only trade. So I'll get rid of all of our stops and strange other devices that we added over here. And I'll add our short exits is going to be our old entries. And then short entries is going to be our old exits. So we want to enter a short position when the RSI crosses above 70. And we want to exit our short position when it goes below 30. You'll see that this is exactly the same as our Quickstart example that I showed you right at the beginning of this tutorial. All we've done is just swapped out the names of these parameters here. So as you might expect, this is a short only portfolio here. So we start off going short, then we close the short, so on and so forth. We repeat ad nauseum as we get through this section of the backtest. We can see that this strategy does pretty well in a falling market, as you would expect from a short-only strategy, but really struggles when we're increasing in price. Now, you're not limited in Vectorbt to going only short or only long. You can do both very easily. So if you had some kind of other indicator in here, you could give, entries is equal to entries 2 here. And exits is equal to exits 2, and that would work just fine, assuming you had separate exits and entries sections. The only thing that you'd have to decide is what you want to happen if a short and a long trigger at the same time. So we can go back here to our portfolio section, and if we go up a little bit, you can see short entries, short exits. So these two options you'll really want to think about. So there's upon direction conflict and upon opposite entry. So I'll briefly explain what these are. So direction conflict is fairly straightforward. Basically what happens if you have a long position and a short position have an entry signal at the same time on the same bar. Do you want the long position or the short position, or none of them? You set that in much the same way as we set our other enum variable. So all you do is you come down here, you forget the name of it. It is direction conflict mode, so it's upon dir conflict. Go back, upon underscore dir underscore conflict, and then we just set that to our enum here. So that's vbt.portfolio.enums.stop. Not .stop exit mode, it is direction conflicts mode. And then we'll pick which one we want. I'm not actually going to run this, so I can pick whichever one. Let's say I want to go with the short signal. So I'll just do short. And now, whenever they both enter in the same bar, which is entirely possible, it'll go with the short option rather than the long option. You'll also want to think about the other one that I highlighted here, which is opposite entry mode. This just helps you figure out what should happen if, say, you're currently in a long position. The long position hasn't been closed, nor is it about to be closed, and you receive an entry signal for the short. What do you want to happen? So the two which are most likely here are close and reverse. Do you want the entry signal on the short to just close out the position? Do you want it to reverse the position like we did before? So you close the position and then you open a short position of the same magnitude? Or do you want to ignore the whole thing? Those are the three options that you're most likely to encounter. There's also these close reduce and reverse reduce options here. These allow you to simply reduce your position rather than closing the whole thing if you have accumulation enabled. So we haven't talked about that, but there's an option over here for accumulation. Maybe I can find it over here. You can see accumulate here. So if we go to the enums for it, you can see that it is possible to set it so that we could continually add to a position if we got multiple buy signals in a row. And so we can simply add to and take from a position rather than just opening and closing the entire thing in one fell swoop as we have been in at the moment. So that's a brief introduction to how the different kinds of orders can be enabled in Vectorbt. I've tried to focus on teaching you how to use the documentation in this section, just because there are so many different combinations of different order types that you might want to execute, that it's very difficult for me to cover them all in just one example. And so I've focused here on teaching you how to read the documentation for the from signals function here. So hopefully you can look through these parameters in your own time and figure out how to use them if it suits you. So for example, the upon opposite entry here, you should be more than familiar now with how to use the enums, how to grab them, and even how to extend that to providing values for each bar by providing an array of integers here. So you could provide an array, and each number in the array would represent a bar, and that would represent, what would happen at that bar if an opposite entry were to be made. And so I hope that's relatively clear. Please do experiment with the different order types I've showed you, the trailing loss, stop loss, take profit, all of that stuff. It's fairly straightforward once you've got all the other stuff under your belt that we've covered previously about how to create indicators and the like. So I'll leave you here for now. And in the next section, we'll be looking at how to make sure that our backtests reflect reality a bit more, rather than just being an overfitting machine and getting lucky with some random parameters. And so I'll see you there for that reality check. In this section, we're going to be doing a bit of a reality check on our strategies that we've devised so far, in that I'm going to be showing you some different methods that we can use to determine how much that we've been overfitting our models, to try and determine whether they're actually useful or whether they're actually generating any kind of edge compared to a completely random portfolio. So just a brief primer on overfitting. It's a concept that you'll come across a lot if you're dealing with data science, machine learning, that kind of thing. And it occurs when you fine-tune the parameters too much to the point that your model only works with that specific data set and it completely fails when you give it any out of sample data. So here, for example, you can see that this function is too simple to explain what's going on. This one is force fit exactly to that specific data set. And this one is about right. It's getting the general trend of what divides the circles and the crosses in this example. But exactly the same thing applies when we're dealing with backtesting and parameter optimization. If you're running thousands and thousands of combinations of different parameters, you're going to find one of them that's done exceptionally well on that particular bit of price data. And so I'm going to show you a couple of methods for reducing the likelihood that you fall into this trap and go live with a model that's just overfit and isn't going to work. The first one that we'll be going through is we're looking at how we can split our data into different windows of time and then test our strategy on all of those different windows. So for example, if we had a year's worth of daily data, we could split that up into 30-day rolling intervals, test it on every single one of those monthly intervals, and we'd have a much better idea of what's going on. And it overall reduces the chance of overfitting because you're testing against lots of different data sets for the same asset. The second method that I'll be using is we'll be comparing the distribution of the returns versus a completely random strategy. So we'll end up with a box plot that looks a little bit like this. And one of them will be our strategy that we've created and optimized. And the other will just be completely random buys and sells. This is very helpful to just have a general look at the distribution generated by your indicator to see if it's actually getting any sort of edge versus a completely random portfolio. So those are the two projects that we're going to be building in this section. You're more than welcome to mix and match them, of course. You could look at the distribution of returns on different sized windows compared to random, etc., etc. I'm going to move a bit quicker in this section than I have in the last couple of sections, mainly because we've seen pretty much all of the basic concepts that I'm going to be using here. So I'm going to go a little bit faster than I did in the previous section. So let's go ahead and dig into the code here and get going. I've got a terminal set up here that we can use. So if I just reorganize my screen, we can go ahead and create our file here. So the first one is just going to be a collection of different windows and comparing the returns that way. So I'm just going to call it windows.py. I'm already inside our virtual environment here, so we don't need to worry about that. Make sure that you've got all the necessary libraries installed as per usual. So we'll go inside our Windows Python file here. And we're going to need all the normal libraries in here. So import Pandas as PD. Import Vectorbt as VBT. Import Numpy as NP. And that should be largely good. We'll also want datetime. And I'm going to be using talib because I already have it installed and it makes calculating indicators and dealing with that side of things a lot easier. You don't have to use talib. You can use the built-in Vectorbt ones that I showed you right at the beginning. So we'll go ahead and grab our data. This should be old hat at this point. So I grab the BTC price data, and that's going to be vbt.yfdata download. And then the symbol. So I'm going to grab BTC USD. Let's drop any missing index. We'll have an interval of 1 minute here. So interval is equal to 1 minute. And then we need a start and an end timestamp. So that's going to be, well, we'll set one to be now. So now is equal to datetime.datetime.now. And then before, so the previous timestamp, which is the the start date of the data that we're going to gather, well, that's just going to be equal to now minus date time dot time delta, and then just days equals 3, let's say. We'll get 3 days worth of data. And then we can plug that straight into here with start is equal to before dot time stamp, and end is equal to now dot time stamp. Okay, so that should be pretty much everything we need there. If we get the closing value, I'm just going to assume that that works, and we'll continue on. Now, one of the main functions in this project, or one of the most important parts, is actually splitting up this data into different windows of time. And helpfully, there's a built-in Vectorbt function for this. So I'm going to go ahead and use that. It returns 2 items, so I'm going to call them BTC price and range indexes. We'll have a look at exactly what they are in a second. And that's going to be equal to BTC underscore price. So we'll take the existing price series that we have, and we'll call .vbt.range underscore split. Now there are 2 parameters in here that you need to think about. N is the number of these windows that you'd like. So you can pick any number you want. I'm going to pick 100. And then you can select the length of the range here. And what that's going to be is the amount of bars in any given window. So I'm going to select 1 for 40. So what this will do is it will select 100 one-day long windows from this 3-day lot of data that we have here. And it'll try to do them at as regular intervals as it can manage. So it'll look at the first day of data, then move forward a few bars and look at that day of data, so on and so forth. I can print them out here to show you what's happening. So if I print BTC underscore price, and then I print the range indexes, we'll get to see what's happening. It doesn't like that I don't have talib. Let's delete that for now. There we go. So we can see the different kinds of objects that we've got on our hands here. So if you remember, I printed out the indexes last, so this is what this is here. And essentially when we look at it, it's basically the names of all of the candles that go into each split. So this one's called split 81, so we had 100 windows, remember? And this is the 81st of them, and this is all of the different candles that went into that particular split. You might need to know this information if you're going to use some kind of function that depends on the time. But largely we'll just want to deal with the actual values themselves. So if I do a bit of scrolling up here, we should be able to get to the actual data. There we go. We can see up here, this is a data frame with all of the different splits in them, just as different columns. If I zoom out a little bit here on my terminal, everything fits nicely. And we can see that we've got 100 different windows, so it starts at 0, of length 1440 from this 3-day range. Now obviously it doesn't have to be a 3-day range, you can use whatever you like. You could set this to download several years worth of data and look at 7-day spans. It all depends on what kind of range you want to be trading. Now that we've got our windows nicely split here into different sections, all that remains is to just continue to build out the custom indicator here and then run it using the indicator factory like we did previously in our parameter optimization section. And we can just pass in the different windows here as the price data like normal, and it'll behave much like it did when we passed in different price symbols. So when we passed in data for Ethereum or Monero or whatever it happened to be, it'll behave much the same way, and Vectorbt will handle it all for us. So the function that we'll just optimize here, we'll just make it a very simple RSI like we have previously. So I'm just going to optimize RSI. It's going to take a close value, a window value, entry value, and an exit value. And then we'll go ahead and calculate the RSI here. So I'll use talib, I'll use the built-in version that comes with Vectorbt. So vbt.indicator factory dot from underscore talib RSI is the function we want, and then like any other indicator factory function, we dot run, we pass in the close, and we also pass in the time period, which is going to be the window for the RSI. So it's going to be window in our case. And then I'm going to grab the real entries from that. So I want the actual numerical values. I don't want a function object. And then we'll just return the entries and exits. So the entries are going to be when the RSI is less than entry, and the exits are going to be when the RSI is greater than the exits. So that's a pretty simple function, but it should serve us well here. We can now just plug that into the indicator factory, easy enough. So my indicator is equal to vbt.indicator factory. We'll give it a name, and we'll call that optimize RSI. And then we'll give it a short name. Just call it RSI. The inputs, so the inputs names, well, that's just going to be close. And then we need to pass in the parameter names. Well, we have window, entry, and exit. So those are just coming from here. And then this is the actual price data. So that gets put in input rather than parameters. This function has two parameters, unlike some of the other ones that I showed you earlier, but broadly it's all the same here when we give it the output names. So I can just say that the first one is going to be the entries, and the latter one is just going to be the exits. And Vectorbt deals with converting this back to a series and making sure the timestamps align and that kind of thing. It seems I spelled entries wrong here. Then we just give it the function that we want to apply it to. So it's going to be from underscore apply underscore func. Well, the function that we want to use is optimize RSI, or the equivalent on your end if you're using some other kind of function. And then we can provide some defaults here for the parameters. So we'll give it window is equal to 14, entry is equal to 30, and exit is equal to 70. So that's our indicator created here. So we've got our data, we've separated it out into separate time ranges, and we've created our indicator factory function here. I'm going to rename it, in fact, to be RSI indicator, just because I'm going to make the random one later, so I don't want to get them confused between the two. Now we need to generate our parameters that we used. So if you remember last time, we used numpy.arrange, so I'm just going to do the same thing again. So entries is equal to numpy.arrange 10 to 45, and the step is going to be equal to step underscore size, which I'll set in a second, and we want the d type to be an int. Again, we've seen this all before, so I'll go through it fairly quickly. And I'll declare step underscore size to be 2 for now. Copy this a few times. We'll have exits. Same thing. And then we want the windows. So windows. And that's going to be very much the same here. So we'll set this to go between like 55 and 95. And there we go. That's all of our parameters up and running. And then all that's left is to actually run the indicator here. So we get RSI results is equal to RSI indicator dot run. We're going to use the Bitcoin price, remembering that that's split into all these different windows. Well, the window value is obviously just going to be equal to windows, and the same for the entries and the exits. And then finally, we need param underscore product. If you remember, that just takes the that just takes all of the combinations of these parameters. It'll just make sure we have every single combination of them, rather than just indexing into each list, one index at a time and moving forward, which means that you don't get every combination. Now that we've got that, we're pretty much ready to run things here. I'll do one or two more tweaks here. So we'll define our entries and exits. So it's going to be RSI entries, and that's going to be equal to results. So RSI underscore results dot entries. Same thing for the exits here. Just use exits instead of entries. And then I'll also set the final exit signal to be true, just so that we close all of our positions out. It's just a bit easier rather than having open positions and then things being a bit complicated. So RSI exits is equal to, or rather, .eloc -1 for all of the columns is equal to true. So this just sets the last element of each column to be true. Basically, we exit the position on the final candle, no matter what, so that we can adequately calculate our total return. We plug this into our standard from signals portfolio. So RSI underscore PF is equal to vbt.portfolio.from underscore signals. We pass in the BTC price, the entries, the exits, and if you want, you can also pass in the frequency of the data here. So usually it can derive it from the timestamps on the associated data that you provide. But in this case, it won't be able to, since the timestamps are obviously different for each window. So we have to tell it if you want to use things like the Sharpe ratio, for example. You have to tell it the frequency of your bars that you're using. So ours is 1 minute. I believe it accepts the standard Pandas date formatting, so T is for minute. I believe capital M works as well. You could also add some fees if you want. So fees would be 0.01. That would be a 1% fee on each transaction, I believe, which is a bit high. So we could maybe make that 0.01. So nothing too revelatory here. We've basically just done our normal parameter optimization, except that we've used this handy dandy function here to split our initial data source into lots of different windows, and then we can view those on the 2D heat map here. Now, since we've got 3 variables here, and we've got like a semi-fourth variable in that we want to be able to look through the different window sections, we'll have to use a volume here to plot this out. Although obviously, if you just want to display 2 variables, 3 variables, you can do that easily with the heat map like I showed you before. So we'll create a figure, and that's going to be pf.total underscore return dot vbt.volume. Then we provide the x, y, and z levels. So x level is equal to, well, it's going to be the short name from up here. So RSI underscore, and then the variable name, so exits. The y level, well, that's going to be RSI underscore entry. And then the z level, well, that's going to be RSI underscore window. Finally, we've got our 4th variable here, so that's going to be the slider level. And for us, that's going to be the column. So I believe the name that it gives it by default is split underscore IDX. You can check that out for yourself by just printing out the total return. It should give you it as a column header, basically, for the series that results. And that should do us really for a simple volume graph here. So I'll do fig.show, and we should be ready to go. Evidently, I forgot an equal sign somewhere. There we go. And it's not Numpy arrange, it's Numpy arrange. Hopefully not too many more errors. Apparently we're getting some kind of error that the entries and exits and the Bitcoin price aren't the same size apparently. So let's print them out and see what's happening. I'll crank up this step size here to be like 10 for now, just so that it loads a bit quicker. We can print out the Bitcoin price, the entries and the exits here. I think I've identified the issue here. It's that I didn't put RSI underscore in front of these. And it was just pulling these values here and trying to match them, which of course wouldn't work too well. So if I press this now, I'm hoping for not an awful lot more errors. Lovely. This is RSI underscore PF. There we go, that's popped up on my other screen here. So what we have is this volume here. So this is the total return. That's the variable that we selected. We can go have a look through different parameter combinations, see what works, what doesn't work. And you can see here all of the different windows that we chose. And this is very helpful for realizing that strategies that work in some periods of time. So you can see that don't always work over all of the different regimes that you're likely to encounter in the market. Now this 3-day period here is not going to cover an awful lot, but there will be uptrends, downtrends, sideways chopping, various kinds of price action. And we can use that to determine if our strategy actually performs well across the different regimes, or whether it's just a one-trick pony and only works in an up or a down market, which is typically not what you want. Sometimes these volume charts can be a bit hard to parse, so I'll just show you how to, say, group this as a 2D heat map instead, if you're more interested in that. That'd be useful if you had two variables that you wanted to optimize, and the third one being the window that you use, the window of time. An easy way of doing this would just be to set our window here to a single value. So I could set that to, let's just say 14, leave it as a normal RSI value. And then instead of plotting the volume here, we'll just plot a heat map. So I'll copy basically the whole thing, except that I'll just change it to heat map. And I'll get rid of the Z level there. And that should work. So I hope that now that you've seen what Vectorbt can do, you appreciate how quickly we can get something up and running. So this might be a bit easier to look at. You can see how the optimum parameter shifts with the time here. So for this section here, it seems the most profitable, although not very profitable, to have your exit very high and your entry very low. Whereas if we keep going, something different might occur. So you can see up here, it's actually better to have a higher entry. And then as we keep going, higher entry seems to prevail. What this is telling us is basically that our optimum parameter isn't overly consistent. It basically changes throughout time. Although it does seem that having a higher exit value is uniformly better than having a lower exit value. So at least you can derive insights like that. Having lots of these windows is very, very helpful to determine how well your strategy actually performs over different periods of time, rather than just overfitting to one area. One other thing we can do here, which I can show you, is we can take the average across all of the windows. So it can be kind of difficult here to see what's going on, what the total return is, and that kind of thing. So what we can do is we can take the average of the total return across each of the windows, and that way we get an aggregated view of what's happening. That can be quite helpful if you're looking to select parameters, but trying to avoid overfitting, basically, if you're using lots of these windows over a good period of time. To do that, we basically just have to have a group by statement. You may or may not be familiar with these from Pandas, but since our total returns here is just a regular old Pandas series, we can use group by on it. So I'm going to get rid of this. I'm just going to say RSI total returns. And instead, I'm going to define RSI total returns over here. So it's going to be RSI total returns. Well, that's going to be equal to RSI.pf.total return. But then we want to apply a group by statement on that. So group by. And then you essentially want to list all of the indexes that you want to keep. So for example, we say level is equal to, well, I essentially just want to keep the entry and the exit. And I want the window to be aggregated with a function that I specify. So the levels, I'm just going to provide RSI exit and RSI entry. And then we need to provide our aggregation function. So I'm just going to say mean, but you can give whatever you want in there. And what that should do, if I get rid of the slider level here, because it won't work, is it'll give us a average view of what's happening. So I can print it out just to make things a bit more clear so we can see the actual series itself. But this is now averaging across all of the different windows. And what we can see is that our strategy is essentially terrible, no matter what combination of parameters that we use. If you average it across all of the windows, so if you were actually running this algorithm for a good length of time, chances are that you'd end up losing money. If you had any sort of fee associated with it, at least. And if you want to see the heat map, it's over here. So you can imagine stacking up all of those heat maps on top of each other and then averaging them down to get the final result here. So that's how to use different windows in order to get a better idea of how well your indicator actually works across different periods of time and market regimes. The final thing I'm going to show you here, just to try and fight overfitting again, is to compare the performance of our returns here against a random portfolio and plot that on a box plot just to see what it would look like. This can often be a good sanity check because if your strategy is not discernibly performing better than random, you probably shouldn't use it. Also worth noting here that I picked total returns essentially at random. You could use things like the Sharpe ratio or max drawdown or any of the other variables I've shown you how to access in the previous few sections. Those would work just as well. So we'll pretend that we've found our optimum here. So our optimum that we're really happy with, and I'll just hard code those in here for now. So we'll say that an entry of 30 and an exit of 70 happens to be optimal for us. We'll say 80 to be more like our results here. So the results of our backtesting, if you remember the heat map, that tells us that we want a low entry and a high exit, basically, to have any chance of making a profit. So I'm going to simulate that here. Let's say that those are our optimal parameters. We don't need param product in there. So with that, we should have essentially 100 versions of this particular strategy being run now that we've identified our optimal parameters. We'll print those out to see just what that looks like. I can probably get rid of this visualization for now. We're not going to be using it. As you can see, we have the exact same parameters. The only thing that's different is this, which just represents the window of time. And so what we can do is we can put that into a box plot, which is fairly easy to do in Vectorbt, much like the heat maps. All you have to do is we'll create a box and we'll set that equal to vbt.plotting.box. And then we'll provide the data. Well, that's just going to be the RSI total return for now. And then we'll provide the names. So in our case, we only have one trace here. So I'm just going to say trace names is equal to, it's going to be RSI strat. And then we'll have to do box.fig.show at the bottom. What this does, if I pull it over here, is it shows us the distribution of our returns. So you might remember box plots from high school maths. Basically, the lines show us the different quartiles and the minimum and the maximum. So the top value here is the maximum value at a whopping 0.28% over the time period. The upper quartile barrier here is at minus 0.7. The median value, so the value which we would expect, is minus 1.2% over a day. And the minimum value is minus 2.5%. So those are the distribution of our returns. We can see it's quite clustered here at about the minus 1% range, which is, I mean, at least it's consistent, but it's not. You don't want to be consistently losing money. So now that we've got that plotted, all that remains is to just create another indicator that just returns random values and then plot that. So I'm going to comment out a lot of stuff and then do some copying and pasting. So we'll comment out all of this essentially from optimize RSI here. And then we'll also comment out the box plot for now because we don't have anything to plot. And essentially what we're going to do is we're just going to copy this whole section. So I'll label this the RSI section. And I'll just copy the whole thing here. So I'll copy all of these. And I'll paste them down here. Obviously, we're going to change these. So this function is no longer going to be optimize RSI. It's going to be a random signal. So it's going to be random underscore signal. It doesn't need all of these fancy parameters. We'll take one parameter, and that's going to be index. We're doing this just so that we can simulate multiple of them, essentially. It's not going to do anything fancy with talib. It's literally just going to return a random signal. So return numpy.random.randint between 0 and 2. So actually between 0 and 1 because it's not inclusive. And then how many of them do we want? Well, we want the length of our price data. So this is just going to return a random Numpy array of zeros and ones, essentially. And we're going to use the ones to represent buys and the zeros to represent sells. So we're completely randomly entering and exiting the market. Let's modify this indicator factory here. So we'll just call it rand indicator. Call it random. Rand. Then we just need to change the parameter name. So it only has one called index. It only has one output. We'll call that signal. The function is called random signal. And I don't think we really need to do anything else. We just need to set the default value of index. Just set it to 1. It doesn't matter too much. We can get rid of all of these. And we'll call this random results. And it's going to be equal to random.ind.run. And we'll pass in the normal BTC price as well as the index here. Come to think of it, we don't really need to pass in any variables at all here, so we can delete that. I'm fairly confident. If we get rid of the index here, it should still work. Since we have everything in separate columns. So we're going to continue our renaming spree here. We'll call this rand entries. And rand, it's going to be equal to where rand dot signal is equal to 1. And then we just repeat down here for the exits. Except it's going to be where it's equal to 0. We continue on. Rand exits. And then rand. Nearly done. Rand. Let's give that a whirl and see if it runs. So I had to do some messing about there to resolve this error. Turns out we didn't actually need the index after all, like I mentioned. The problem was that the returned value here of this function wasn't the same as the one being inserted. When I'd ran this previously, I was just using a single column of data. Now obviously we have 100 columns. So to fix that, I just added size is equal to close.shape here. And that'll just ensure that whenever it generates these random signals, it's exactly the same shape as the input data. Everything else should be pretty much the same. Very simple indicator factory. We're just literally saying what the input and the output is. No parameters at all. We can actually get rid of index there in the function definition. I missed it. The indicator.run section here, just very simply passing in the price. Then when the signal's 1, that's an entry. When it's an exit, that's 0. Make sure that we exit our positions at the end. So on and so forth. And then we can plot this here just to show what it looks like before we combine them all. So it's going to be rand, and it's going to be the random data. So I believe this should work if I just press go here. Ah yes, I forgot to remove this again. We don't need the index at all. I can pull this over now and show you the results of just randomly trading. We seem to be losing pretty consistently about minus 0.5%. That's likely due to the amount of trades that we're doing. To make this more fair, you can get rid of the fees here, or you can devise some scheme to make sure that the random trading is not trading too often. So to add in the other trace here, very simple now. All we have to do is, well, we firstly have to go and uncomment all of this stuff. Uncomment the RSI section here. And then remember the variable name here, RSI total returns. And the easiest way I've found to do this is to just make a new data frame. So we'll just call it df is equal to bd.dataframe. And then we just set the columns to be the values. So we'll have RSI is equal to RSI total returns, and random is equal to rand total returns. And then we'll close that out. You'll want to convert these to lists or Numpy arrays or something of that sort, just to make sure that they're flat and one-dimensional. So we'll convert them to just regular old Python lists here. Data frame should be able to take that in. And we'll give this df instead. And we'll give it the labels RSI and random. One thing it's worth doing here is printing out the median values here. So I can print out df.median. The reason I'm doing that will become apparent in a second. So if we run this here, we should be able to compare between the two. As you can see, the random here is doing significantly better than the RSI. You can check the median values here to make sure that you've labeled them correctly. You really wouldn't want to get them the wrong way around. Looking at its performance, you probably wouldn't want to run this strategy anyway, but if you had any doubts, then comparing it to the random one here would let you know pretty quickly that it's probably not the right strategy to run live. And this is why we do all of these comparisons here. If you'd just taken the overfit value from the full data set, you might be under the impression that you're going to get a 3% return daily forever, when actually when you average it over all of the windows and you look at the total distribution here, you see the results aren't so stellar. Do make sure that the portfolios here have the same settings, that you're not unfairly biasing one way or the other. And with that dose of reality, that is us done for this tutorial. So that's the end here for this tutorial. I hope you got something from it and you learned a great deal about Vectorbt and how you can use that to produce profitable strategies of your own, or at least eliminate the ones that really aren't doing too well. If you want to get the full code for all of these tutorials, they're available on the blog posts in the description below. just in case you can't find a nasty spelling error or something. There'll be up-to-date versions of the code available on the blog or on my GitHub. So I hope this tutorial has helped you out, and good luck in the markets.